All right, well, good morning, everyone. So really excited that you're all able to make it to our workshop on mesoscale and frontal-scale air-sea interactions and their influence on Earth's climate. So my name is Larry O'Neill, and this is Hisashi Nakamura, and we're the co-chairs of the workshop. And once again, really glad you all can make it, and we're really glad that we're having this nice virtual opportunity so that we people who can't make it can still attend virtually and get in on all the excitement and action. So this workshop is sponsored by the US CLIVAR working group on air-sea interactions, and US CLIVAR itself is funded by, supported by NASA, NOAA, NSF, and DOE. So we want to acknowledge our sponsors and for providing travel support to everybody, or to most people, and so we're really glad you can do it. And I also want to acknowledge our science organizing committee that has put together the workshop. Allison Cobb, Baylor Fox Kemper, Ivy Frenger, Sarah Gilly, and Justin Small. So really appreciate all the efforts. And we really appreciate the participation in such a short order. So due to a lot of scheduling constraints, we weren't able to set the date, finalize the dates until December. So we're really glad that everyone was able to come up. So we're just going to give a very brief overview on the our air-sea interaction working group and just some of the goals of the workshop that we're doing. So this US CLIVAR working group, we formulated it back in about 2019. I think it was 2019. And it was basically to bring together a community and synthesize a lot of the advances we've made in air-sea coupled research, specifically on the mesoscale and frontal-scale, and try to combine communities that were working on different threads of research towards that goal, with the idea that we wanted to kind of get a broader view, broader synthesis on how things like western boundary currents, ocean eddies, interacted and how they influence the Earth's climate, how they influence the ocean structure, and a lot of this broad interdisciplinary research here. And so some of our specific objectives that we had for this working group was to produce a review paper synthesizing current understanding. And we've just recently, it's going to be published officially in the Journal of Climate on April 1st. And so this brought together, it's a review paper that synthesized a lot of the advances that have been made in the last 10 years. Since the time we've had a few earlier review papers in the 2000s and early 2010s. And so this paper kind of expanded on that with a lot of the current research that we've been doing. Another goal of the working group was to develop diagnostic frameworks and analyze models and observations. And so this is a really key goal that we had. And this is one of the reasons we're having this workshop here, is to bring together a lot more researchers and practitioners in the field to better make sense of observations and models and build new paths forward on how we can do this. And finally, we want to identify consensus on uncertainties and directions forward for observations and modeling. So right now is actually a very exciting time in air-sea interaction research. We have a lot of planned missions or proposed satellite missions, in situ monitoring missions, and the development of new and much more sophisticated climate models and weather prediction models here. And so this is a very exciting time, and so we're trying to kind of have efficient paths forward for how we utilize these to all these tools, all these observations, and all these new advances to understand Earth's climate better on this. So we have for our working group, we have about 18 members. So 12 of those are from the on the US side. So this is a US CLIVAR working group, but we also have international contributing members as well that I want to acknowledge on this slide. And this just in a kind of a, going back to a broad, a very broad goal of this working group, it actually addresses many research topics that are covered under US CLIVAR, which includes seasonal, subseasonal prediction, decayable variability and predictability, climate change, climate and extreme events, both in the weather, both in the atmosphere and the ocean, polar climate changes, climate and marine carbon and biogeochemistry, and also climate at the coast. So the coastlines are a big effect on civilization here. And this working group actually overlaps with all these different missions. And it also, as a bonus, has affects some other things that are very important as well, including Earth's hydrological cycle, so this distribution of precipitation, the occurrence of droughts and things like that. A new topic, marine heat waves, both in the coastal and open oceans, and also in ocean ecology and biogeochemistry. And so the distribution of fisheries and productivity there as well. So this working group and all of the members here span all these disciplines here. And so a big goal of this working group and this workshop is to get discussions and also kind of synthesize a lot of this information, put together in white papers, and present it to program managers and agency heads here, and to help chart the course for the next decade or 2 decades of research and observation. So this is the review paper that I talked about that we produced as part of our working group, and Kyode Seo led the effort in publishing this. So this will come out in April 1st here, and thanks to CLIVAR, this is open access, so anyone can get this. There's no paywall behind it. And we have this nice little QR code that we're going to put up somewhere so that you can just scan it and get to the paper page right away there too. So the workshop objectives that we have for today is to engage all of you in the research and operational communities spanning a lot of different disciplines and sub-disciplines of earth science. And we seek to solicit feedback on the state of the science. And we want, so us as the organizing committee and us as the working group, we are now very much in the listening mode. So we want to hear more about what you have to say and what your ideas are and what your new research findings are and what your research challenges are. We want to identify key gaps in understanding, specifically around mesoscale and sub-mesoscale air-sea interactions. And we also want to provide recommendations for pathways forward to improve our modeling and observational capabilities. So the themes of this workshop, we've identified in the review paper several themes after much discussion between ourselves and with other members of the community. And so we've got 6 sessions that we'll be looking at, and there'll be 2 for each day. So today we're going to go through our first session. We'll be looking at the boundary layers and surface heat, momentum, and gas fluxes on the ocean mesoscale. And the reason we do this first is because this is what sets the stage for all the air-sea coupling. So it's this exchange of heat and momentum with the atmosphere and ocean, and this really sets the stage for how the atmosphere responds, how the ocean responds, and what the couple feedbacks on each fluid are. And then after break, we're going to look at the free tropospheric and extratropical atmospheric circulation responses. So we're going to see how this air-sea coupling is affecting our large-scale atmospheric climate and weather. And then we'll have sessions in the following days on the feedback of the atmospheric responses onto the ocean. And then we're going to look more specifically at the state of our current modeling capabilities and our observational capabilities here. And this session 6 is kind of more of a forward-looking session. So we're going to look at what future strategies we might employ to improve observations and modeling. What now that we have identified some key gaps and some key questions, what strategies can we look at going forward to address those here? And so our workshop outcomes, we're going to write a synthesis white paper on all the discussions. So we'll be taking lots of notes. We're going to try to engage in discussions in some of these breakout sessions in the afternoon. And we're going to synthesize this all down into a white paper. And this white paper will be used for, that will present to CLIVAR, to some of the interagency program managers, and to look at what the community is thinking about in terms of mesoscale interaction. What is it we need? Where are the challenges lie? And also, what do we know? And we're also going to have, hopefully, have some sort of workshop paper that will be published in BAMS, the Bulletin of American Meteorological Society, and it'll be kind of just outlining some of this to other communities as well, so that other communities are aware of what we want to do and where we think this is going. And hopefully that will help build some bridges into other sciences. And also, and as always, for every workshop, this is, not many people have gone to COVID workshops post-COVID. So this is a great opportunity to make new friends and have a good time blinding each other with your science. So, so please have a good time with that here. And Xiaoqi will take over, discuss a couple other things as well.
Yeah, so we have like very quick statistics for the participants here. So this pie chart basically tell you that we have a 60% of online and in-person participants are early career students and early career members. So this is actually really great that we have this young next generation scientists participating in this workshop, interested in Earth interaction problems. We have very diverse countries as well. So 15 different countries participating from this in this workshop. So this is great. So this leads to sort of code of conduct. Basically, we all know how to behave in the workshop. We want to be inclusive and kind to each other. So, and if there's anything that you want to report, you can talk to either Larry, me, or there's a US CLIVAR organizer, Mike Patterson, and Sam Coakley in the back. And please talk to us if you see anything. So here is Sam, you want to talk about this, maybe logistics?
Sure. Thanks, Xiaoqi. So hi, everybody. You've probably gotten too many emails from me. I'm Sam Coakley from the US CLIVAR project office. So thanks, everybody, for coming. I just wanted to address a couple logistical things. I'm sure for everybody in the room, you've probably already figured out how to get on the Wi-Fi. There's no password needed, but it's just UCAR visitor. If you haven't noticed, the posters are going to be on the catwalk on the second floor. There's stairs just on the other wall when you walk out of the plenary room. For all of the people online, if you have any questions or issues, technical issues, please feel free to reach out to me on WebEx. That'll be the easiest way to get to me rather than email, or Kelvin on the WebEx as well. It's our IT support. So feel free to send me a private message there. And then for everybody in the room, please be considerate of the virtual participants. They can't hear you unless you are speaking into a microphone. So speakers, make sure you're facing that podium mic clearly. And then when we're doing open discussions, or if you have questions during after the talks, please go up to the standing microphones that you can find in the aisles. And that's the only way that the people online will be able to hear you and participate. Do you have anything to add, Mike? Oh, yes. If you need an elevator to get up to the second floor, please come to me or Jessica Martinez, our meeting planner, who's out at the front, who you've probably already met. And that's all for me. I
think session chairs will be also moving around the microphone if there's multiple questions from here and there, so we can facilitate more discussion.
Well, actually, it might be preferred to have people lined up. Yeah, it's just so we can keep the queue straight.
Okay, that's fine. Yeah.
With this large of a room.
I guess that's all we have. So yeah, we can start the first session.
Okay. So, all right, so we're going to dive right on into our first session. So the first session is on boundary layer heat, momentum, and gas fluxes. And so we have a couple talks here that will talk specifically about some of the exchange processes and kind of summarize, and some of the impacts that it has on both the atmosphere and the ocean. And so our first speaker who will be talking to us is Lucas Laurindo. He's from the University of Miami, and he's going to talk to us about a brief overview of air-sea fluxes of heat, momentum, and gas tracers at the oceanic mesoscale. Thank you.
Thank you. Okay, good morning, everyone. It's a pleasure to be here, quite an honor. And okay, so
you can get a little closer to the mic, please.
Okay, is this better? Okay. Okay, the surface fluxes are fundamental quantitative indicators of the coupling between the ocean and the atmosphere. And a traditional view in climate dynamics is that the surface flux variability predominantly arises from the action of intrinsic atmospheric processes. However, it has become clear in the past 2 decades that mesoscale current and SST features can induce significant surface flux anomalies, which have feedback to both oceanic and atmospheric situations. So the objective of this presentation is to revise the knowledge on the variability or RC fluxes of heat, momentum, and gas at the mesoscales. Starting with the turbulent heat flux variability, I'm showing here the bulk formulas. When I'm talking about turbulent heat flux, I'm talking about the sum between sensible and latent heat fluxes, which I'm showing the bulk formula right here. They're both proportional to the wind speed in red and to the RC contrast of temperature and humidity. Sorry. And for the figures that I will show in this presentation, I defined the heat fluxes as positive upwards out of the ocean. So positive values mean that the ocean is cooling, and negative values mean that the ocean is gaining heat. And as I mentioned, the community usually assumed that variability in the heat fluxes was mostly driven by weather. In the 70s, Klaus Hausmann introduced the stochastic climate model theory to explain how chaotic day-to-day weather variability in the heat fluxes could lead to SST variability on the scales of years to decades. And the theory has been very successful in representing the SST power spectrum in mid-latitudes, as well as the shape of the lag correlations between SST and THF. And where the theory is valid, we can expect near zero correlations between SST and THF at lag 0, and negative correlations between the SST tendency and THF. And indeed, couple simulations and observations of the time showed results that did not resolve the effects of ocean mesoscales, resolve this type of relationships. But in the past 2 decades, after the 2000s, satellite observations increased resolution, and we could also have simulations with higher resolutions in the ocean, in the atmosphere. And this picture changed. We now resolve positive correlations between SST and THF over much of the extratropics, coinciding with strong current systems. In the SST tendency and THF correlations actually diminished to near zero or the same regions. And recently, we had studies that extended the stochastic model theory and to include the action of ocean processes. It could attribute these positive correlations to the action of intrinsic ocean processes. And these same studies also showed that these positive correlations, depend on the spatial scale that you're looking at. So I'm showing, try to reproduce here using CSM high resolution simulations. And if you filter the data to isolate only the light scales and recompute the correlations, it drops to almost 0. So we end up with a picture that looks much like what a eddy parametrized low resolution simulation resolves. And if you do the opposite and isolate the mesoscales, you have positive correlations almost everywhere. And now this is the same, but for the SST tendency and correlation. If you isolate large scales, you increase the magnitude of the correlations, which become deeper pretty much everywhere in the ocean. And at the ocean, and this also looks as the low resolution simulation. And if you isolate the mesoscales, you end up with near zero correlations everywhere. And this implies that the atmosphere drives the variability at large spatial scales, while the ocean process dominates the variability at the mesoscales. Another way to look at this is to look at the variances. This is the ratio between high and res resolution CSM simulations. And where the colors are warm, it means that HR has more variance than LR. And the color scale here is logarithmic, so a value of 1 means that HR has 10 times more variance than LR. So this, the top band is for SST, the bottom band is for the heat fluxes. They're very similar, so this is consistent with the interpretation that the ocean, resolved ocean processes drive SST anomalies that induce a response to turbulent heat fluxes. And to see where these higher variances, the scales where these higher variances are located, we can take a look at the power spectrum that they're resolving. So here is for spectrum as a function of zonal wavelength for the Agulhas return current. Red is SST, blue is for turbulent heat fluxes, and the dashed lines is for the low res, the continuous is for the high res, and the dashed dot is for observational product, the geophotography. And you can see that at large scales, the longest wavelengths, they show similar power, but as you go towards smaller scales, like the variance in LR just diminishes, where the variances in HI and observations remain high. So this feature here is not resolved by the LR. Regarding the time scales of the variability, the recent literature showed that the weather dominates the variability at a higher at monthly or shorter time scales, and the ocean tends to dominate the variability over longer time scales. So here, this is from a paper me and my colleagues published recently, which I think illustrates these. The gray line is the power spectrum for turbulent heat fluxes in the South Pacific. And I tried to break it, this spectrum down into atmospheric-driven and ocean-driven components, atmospheric in red and ocean in blue. And you can see that the atmosphere dominates at the high frequency end of the spectra, while the ocean dominates over lower frequencies. And the panel B here, if you filter the data to isolate just these scales smaller than 10 degrees, we end up with a spectrum that's essentially driven by ocean processes. Okay, so now let's move to horizontal momentum flux. The ocean and atmosphere, they exchange horizontal momentum via the stress of the wind acting over the ocean surface. And at the mesoscales, the stress is influenced by the mesoscale SST coupling because of the anomalous heat fluxes, which modify mixing pressure gradients within the boundary layer, which drive the wind anomalies. And the stress is always modified by the surface ocean currents because the wind does not act at a static surface. You have currents that the surface of the ocean is in motion. And start with how to characterize the SST-induced response in the boundary layer. We usually characterize it by linear regressions between SST and either the 10-meter wind speed or wind stress by positive correlations. But to tease out the signal, you need to filter the data in space to isolate scales smaller than about 1,000 kilometers or smaller. And many studies also smooth the data in time or average it over the time scales of a few weeks. And this figure is from the paper from SEAL 2017. And you can see that the positive correlations are pretty prevalent. You can see over most oceanic regions. And you also develop positive correlations between the downwind component of the SST gradient and the wind curl and the wind stress curl. and positive correlations between the crosswind component of the SST gradient and the wind stress divergence. Another common metric is the correlations between Laplacian of SST and the Laplacian of sea level pressure is used to tease out the pressure gradient mechanisms that arise in response to SST anomalies. And even though those are very simple metrics, simple correlations, it has been very useful to assess and guide model development in the past few years. And alternative approach to time domain regressions, it's one that I'm very biased towards, but it's using spectral methods. And it's useful because you evaluate how any two variables are linearly related to each other along a range of spatial and temporal scales. So you don't need to rely so much on spatial filtering and temporal filtering. For example, this figure here is showing the coherence, which is like a regression coefficient, but as a function of the spatial scale or temporal scale for the Pacific, and also as a function of latitude. And you see that the signals is very highly related at large scales, but as you go towards smaller scales, it changes the behavior. This panel on the right shows the phase relationship between SST and winds, and you can clearly see a change in the relationship here. It comes from 180 to near zero values. So what you're seeing here is the shift from a large scale atmosphere-dominated regime into the mesoscale regime, where the SST anomalies can affect the atmosphere. This phase information is also important because the perturbations in the atmosphere are not just sitting on top of the SST anomalies, but they, here I'm showing a figure from a paper from Niklas Schneider, 2020. And these circles here is a Gaussian idealized SST anomaly. And the colors and the vectors are the wind anomalies that are arising associated with that, with the winds blowing here from the left to the right of the figure. And you can see that the wind anomalies are not just sitting there. You also have modifications at the downwind direction of the anomaly. And what Niklas, Dr. Schneider did is he uses spectral transfer functions to reconstruct this dynamical response, something that you cannot really do if you just use time domain regression coefficients. There are a few papers that started to show that this SST induced response to the marine bound layer also occurs in the sub-mesoscale ranges. I'm showing one of these papers here from Gob et al. 2019, which use a very high resolution satellite sensor, the Aster, to show the SST associated with a sub-mesoscale filament over the Gulf Stream, and show that it had like a wind anomalies sitting on top of it. Another paper, Mironi et al. 2020, showed that the usual metrics that we use to show this response might not work at the sub-mesoscales. It suggests that a better metric might be using the linear relationship between the wind divergence and the second derivative of the SST. Okay, so now the influence of ocean currents on wind stress. Accounting for this influence usually results only in a small correction in wind stress, because winds are usually so much faster than currents. However, this has a very large influence on the wind stress curve. It can affect the low-level wind shear, and also creates a sink of kinetic energy for mesoscale eddies. A signature of this influence can be seen by negative covariance between surface geostrophic currents and wind stress, which I'm showing here. This figure is from the paper from Rai et al. 2021. which filter the data to isolate scales smaller than 250 kilometers. And you can see that the covariances are predominantly negative, where you have strong high eddy kinetic level levels. Something that I thought was cool about this paper as well is that they evaluated the the spatial scale dependency of the relative stress effect, and found that they occurred mostly at scales smaller than 250 kilometers. Now, it's not trivial to separate the influence of SST and currents in wind stress. That is because the regions with high SST variability, they coincide with regions with high current variability, implying that both effects can be correlated with each other. And Renault et al. 2017, they investigated this issue and concluded that you could isolate the influence of ocean currents by using regression coefficient between the wind stress curve and the surface current curve. Finally, mesoscale ocean features can also impact the air exchange of gas tracers. The flux can be estimated by this expression, which is proportional to the gas transfer velocity K, and the difference between the gas concentration at seawater, C, and CQ, which is the concentration that it should have if the water passes equilibrium with the atmosphere. And studies have shown that mesoscale eddies can modulate the fluxes of gas by influencing the solubility of trace gases, affecting the primary productivity associated with eddies, or by the influence of the eddies over the winds. And one of such studies is from Pezzi et al. 2013, that is reproduced by the review paper, which shows where they measured traverse a warm core edge using ship, and they measured a clear signal of CO2 associated with the eddy. And despite these results, current available assessments of large-scale based into global scale suggest that this effect, this influence on the CO2 positive and negative mesoscale anomalies of CO2 fluxes, they might cancel at large scales. Okay, sorry for running long. That's all I had. Thank you very much.
So I think what we'll do is we have a discussion period in at 9:20, and so maybe we'll hold most questions for then.
I was just trying to remind you to use a mic. So yeah, I think we can hold questions until the open discussion and move on.
Great.
Okay, thanks so much.
Okay. All right. So our next speaker this morning is Niklas Schneider from the University of Hawaii, and he is going to talk about the Gulf Stream Convergence Zone. So thank you.
Work.
Okay, just advance it.
Oh, pointer? Oh, pointer.
Pointer is there. Yeah.
Pointer. Okay, good morning. Thank you very much for the opportunity to speak to you this morning. It's a great pleasure to see you all. I hope I'm coherent. I just got in. It's not that far compared to a lot of people in the audience. I just come from Hawaii, but I came in at 2 a.m. Not scheduled, but so I hope this is going to be coherent. So I'm going to talk about the Gulf Stream Convergence Zone, and that's a name that was coined by Larry O'Neill in a 2017 paper, and it describes the dipole of surface wind divergence that we encounter over the western boundary current here in this example over the Gulf Stream. So what you see is in the contours is sea surface temperatures. You see the Gulf Stream front in the Northwest Atlantic, of course, and the colors are surface wind divergence, with the hot colors being positive values of divergence, the blue colors, the cold colors being negative values, and you have this nice dipole. Both of these variables are based on satellite observations or long-term averages, multi-year averages. We have this, again, this dipole across the Gulf Stream with positive values on the cold flank and negative values on the warm flank of the Gulf Stream. Now, if you look at this, per se, you would say, okay, of course, that has something to do with the sea surface temperature. And indeed, if you run atmospheric general circulation models and withhold this frontal feature in the sea surface temperatures, then you fail to simulate this dipole. So it has to do something with the sea surface temperatures. What I would like to show you today is that this dipole results from a collaboration or the combined action of the storm track, the transient winds in the storm track, and the boundary layer dynamics. Let's just set the stage what we have. So just remember the order of magnitude that we see in the mean is about half times 10 to the minus 5 inverse seconds for the divergence. And so in the following, we'll just focus on this longitude band between 52 and 62 west as a function of latitude. And if we just look at this band and simply look at the scatter plot of the wind divergence in the vertical axis versus the downwind gradient of sea surface temperatures, which is one of the metrics that Niklas just mentioned for the vertical mixing process in the boundary layer. So if you look at the scatter plot, you see this very nice distribution. Note the vertical axis of the wind divergence. It's of the orders of 10s to 20s times 10 to the minus 5 inverse seconds. So this is what we have to deal with in this area, that we have the mean of the order of 0.5 times 10 to the minus 5 meters per second is embedded in this enormously large variability. Furthermore, if you look at this dashed line, this is the ensemble, this is the bin average as function of bins in downwind sea surface temperature gradient. You see there's a nice relationship between the wind divergence and the downwind gradient of sea surface temperatures. The slope of this line is the coupling coefficient that Niklas just mentioned. But you notice that if you go to the very large values of the downwind gradient of sea surface temperature, that this slope is different for positive and negative values of the sea surface temperature gradient. So there's a nonlinearity in this process. Of course, in the following, we'll look simply at the mean Gulf Stream front and we compare it to the mean sea surface temperature gradient. That indicating, and if you see these red tick marks at the bottom axis, this is sort of the order of magnitude of the mean sea surface temperature gradient Gulf Stream front. And so that's actually much smaller than the extremes that we see, and we'll just look at the linear relationship in the following. You notice also, again, the mean is hard to see. Actually, you can't really make it out on this. So the mean is a tiny residual between these very large values of wind divergence that are associated with the sea surface temperature gradient, and much more important also with mid-latitude cyclones and atmospheric fronts, as I'll show you next slide. And also you notice that this distribution is highly skewed. It's skewed negatively. And so that results in a difference in mean and median that's shifting towards negative values. That indicates that the very large amplitude processes like mid-latitude fronts and cyclones have an impact on the mean. You also notice, I would note that as a function of sea surface temperature, even for the very large values, you can see the impact of sea surface temperature gradients. It's not that the large values of surface wind divergence or the negative surface wind divergence of cyclones are independent of sea surface temperature gradient, but you see that asymmetry in the distribution as a function of the sea surface temperature gradient very clearly in this plot. Okay, so let's just see what we are dealing with actually with these very large values. And of course, this is associated with fronts and eddies. So if we simply look at the very large values, in this case of the negative values of the surface wind divergence, larger than minus 20 times 10 to the minus 5 inverse seconds, and do a composite. And we don't just do a composite, especially composite based on the surface wind divergence, but in addition, we composite it by the wind direction at the center point of this frame. And so what you see is, you have four different plots here. The top left is the composite, again, for very large values of negative surface wind divergence at the center point, where you have this red dot, which is the surface wind divergence. And it's composited that the surface winds are from a northeasterly direction. The bottom left, the winds are from the northwesterly direction. The bottom right, winds are from the southwest, and the bottom left is from the southeast. So you see very nicely, of course, I arranged them that way. It's always a cyclonic circulation. It's always a cyclone, and you can actually make out, if you are so decide, in this very average issue, in this very average plot, you can make out something that might look in the top row like occlusions or warm fronts. If you compare the wind directions where the minimum is, with the location of these of the hotspots, and in particular the change of the winds. That looks like an occlusion or warm front, and the lower one looks like a cold front, particularly the lower right. It's really looking like a classic cold front with a strong change in the winds from the cold sector to the warm sector. So quite clearly, these large values of the surface wind divergence are associated with cyclones and fronts. Now, how about the overall boundary, the hypothesis for the Gulf Stream convergence zone that I'd like to follow here? So we basically dealt already with the left arrow, that we say if the mean value of the surface wind divergence is informed by simply the storm track, by the transient variations of cyclones and front in the surface wind divergence. But how about the impact of the sea surface temperatures? And so there I would like to show you that this impact on the surface wind divergence is informed both by the sea surface temperature gradients, of course, and also by the transient winds associated with the Gulf Stream. It's very important that we have this. Okay, so let's have a look how that works. So for this, we need a boundary layer model. And this is related to what Lucas just mentioned in terms of these non-local relationships between the surface wind and the sea surface temperatures. You look at the classic description like a coupling coefficient, as I showed you in the second plot. It's a local relationship between the winds and the sea surface temperatures. Now you can extend that and say, okay, we look at the relationship between the winds, in this case the wind divergence, and the sea surface temperatures, but we extend that to the sea surface temperatures everywhere. Right? And so then we have basically a lagged regression where the winds at a particular locations are again a function of sea surface temperatures everywhere, with these regression coefficients, if you want, or impulse response function being this A. Now, the important part of this is A, depends, of course, on the lag. And the lag itself depends on the large-scale wind. It makes a difference whether the sea surface, if you're interested in the winds at a particular location, whether the sea surface temperature is upwind or downwind or crosswind from you. It also depends on the speed of the large-scale winds, simply because information travels further for stronger winds. So this is an expansion of the concept of a coupling coefficient. It's simply a lagged regression, if you want. And this is related to the spectral approach that Lucas just mentioned. This is simply the inverse Fourier transform of the spectral transfer function, the impulse response function. So it's the same sort of thing. So I estimated these lagged regression, this impulse response function from satellite data. Again, for a long period, you have to do that for daily data, because you want to have the transient winds, the information of the transient winds enter. And what is shown in the bottom 4 plots is exactly this impulse response function, this A. So it has 4 panels from 1, 6, 11, and 16 meters per second as a function of large-scale wind speed, so that U dependence. Then each of these boxes is a plot with lags. The x-axis is the lag in the direction of the large-scale wind. The y-axis is a lag perpendicular to the large-scale wind. And what's shown in colors is the impulse response function. So you could say it's something like a lagged regression. And it's shown it's basically formally, it's a response to a delta function, sea surface temperature at the origin with a particular strength of impulse of 1 Kelvin per square meter. So let's just look at let's say panel C, that you see, okay, so the delta function of the sea surface temperature is right at the origin where these 2 dotted lines meet, and upstream and downstream of that is a dipole of sea surface temperature, of surface wind divergence, which is exactly what we described from the coupling coefficients. So the sea surface temperature gradient, downwind sea surface temperature gradient, is related to the divergence of the surface winds. But you also see a lag that extends in the downwind direction for hundreds of kilometers. It scales with a sort of a distance traveled in half inertial period. And you see a strong asymmetry that the response is stronger on the left side if you look in the downwind direction as compared to the right side in the downwind direction. And so this is, if you compare that with this theory, if you want, that we developed about 7 years ago now, my goodness. So this is consistent with a damped Doppler shifted near-inertial wave in response to changes in vertical mix in the hydrostatic pressure associated with this plume of warm air that emanates downwind of the sea surface temperature perturbation. The important thing is that it includes both the vertical mixing and the pressure effect. Vertical mixing is basically the dipole, and the pressure effect gives you the asymmetry of the dipole in that you see that downwind pole has a larger magnitude than the upwind pole. So both of these effects are in there. They have different scale dependence. So this is our boundary layer model. And so now we are coming back to the Gulf Stream convergence zone. And so we'd like to represent our surface wind divergence via this convolution, simply the same approach that I just showed you, We just say, now, okay, we want to reproduce the surface wind divergence based on these impulse response functions that we derived from observations, but now applied only to the Gulf Stream front. And we take the mean Gulf Stream front, time average Gulf Stream front, which is that red line in the lower plot. Vertical axis sea surface temperature in units of 10 degrees Kelvin. So it's about a 15 degree Kelvin temperature difference across the Gulf Stream in this red line. The black line is what we want. The black line is the surface wind divergence across the Gulf Stream front with this dipole, positive values on the cold, negative values on the warm flank of the Gulf Stream. So we want to calculate that basically with this convolution. But again, note, in order to do that, we have to take the average. Right? We want the average surface wind divergence. We already take the average of the sea surface temperature front. So we have to take the average of the impulse response function. Again, that depends on the daily changing wind speeds. So we actually have to calculate that by accumulating its response based on the probability density function of the daily averaging winds. And so what I'm showing you here, again, this formulation for the mean impulse response function as a function of the instantaneous impulse response function integrated over the probability density function of the large scale wind with direction EU and the speed U. And what's shown in the plot is simply the windrows of the large scale winds over the whole year. So both seasonal cycle and their synoptic variability. Basically what you do is, so for every of these spins, you rotate and interpolate the impulse response function to the direction of the winds and the speed of the winds. You save the results, and then you add up all these results for all these different spins, weighing them by their relative contribution, by their likelihood. Okay, so if you do this, this is what you get. So this is again, oops. So the red line is the sea surface temperature, the black line is what we want, the observed values, and the dashed line is what you get from this reconstruction. And of course, I would argue you do pretty well in terms of both the location and the magnitudes of the sea surface temperature of the Gulf Stream convergence zone. So let's just play with this. So the difference between these two, of course, our linear approach has no information about the bias that's introduced by the cyclones and fronts. So if you take the difference, the residual between the reconstruction and what we actually have, then that should be a measure, or is influenced by the residual convergence that's induced by the fronts. And the only thing I would like to show you here, it's negative. It's always biased negatively, as we expect from cyclones and fronts, and even of the order of magnitude scales with a difference in medium. So that's at least consistent with this dual impact of the storm track by giving you a bias due to cyclones and fronts and this boundary layer response that we're capturing with this approach here. Okay, so you can also do conditional averages and say, okay, well, what happens to the averages if we don't do a long-term average over the Gulf Stream front, but we condition the averages, which depending on the direction of the wind relative to the sea surface temperature front. So in our case, with a very simple Gulf Stream front, that means we look for the wind divergence when it's northerly winds or southerly winds. Northerly winds, the winds go from cold to warm. Southerly winds go from warm to cold. The solid lines are the observations, and you see this strong difference between these two averages. The dashed line is what we get from this reconstruction. Again, the dashed lines know nothing about the bias of the included by fronts and cyclones. But still, I think it's a reasonable depiction of these conditional averages as well. So we capture both the long-term averages as well as the conditional averages. That's already a long list of conclusions. So I would like to convince you that the Gulf Stream convergence zone results from cyclones and fronts associated with the storm tracks and from the aggregated response of the atmospheric boundary layer to the SST front and to the large-scale winds associated with storm track. And the reconstruction is successful in getting the dipole. It gets the residuals that's consistent with cyclones and fronts. The conditional averages are reasonably depicted. Two things I haven't shown you. You can, of course, it's a linear model. You can say what's the sensitivity to SST gradients. If we degrade it, then of course it's a linear model. If you withhold variance at high wave numbers, you don't get them in the result. So of course we recover the observed sensitivities. And you can also argue why the pressure effect might emerge for long-term averages, which I'm not showing you here. I think for this group here, maybe the implications and limitations of what I'm showing you here. So it's a non-local approach. And it only captures the linear of, if you think of a Taylor expansion, and a first order dynamics. We capture both vertical mixing and pressure effects, and the transient winds are the ones that organize the boundary layer responses. The average combines the boundary layer responses, the large-scale wind probability density function, and the geometry of the SST front. So it's not obvious how that comes out for every western boundary count. So in our case, we have as a particular boundary layer response, a particular PDF of winds, and basically a north-south front. And so that the combination of all of these, that gives you the averages, not just the boundary layer response. And then, of course, we only have a linear response. So the basically very strong linear processes like boundary layer height response, precipitation, and also in winds, if advection by SST-induced winds are important, that's not captured. And of course, I very blatantly relegate the feedbacks to the large scale and transient winds by the SST fronts to higher order processes. And that's, I think that's something that we'll discuss at length in this conference. Thank you very much.
Yeah. It's like age. You so. Okay. I want to introduce our last speaker of the session. It's Leah Johnson from the University of Washington, and she will talk about multi-scale turbulence in the ocean surface boundary layer. So that's the button for the point. Thank you very much.
Right, I'm at the Applied Physics Lab at the University of Washington, and this is work that I'm doing with Baylor Fox-Kemper as a part of a general goal of evaluating the fidelity of ocean surface boundary layer turbulence parameterizations, and in this rendition, how well those parameterizations capture fine-scale turbulence in really in the presence of sub-mesoscale flows. So the ocean surface boundary layer is really defined by the processes within it that redistribute heat and momentum and buoyancy throughout that layer. This is generally done by surface forced turbulence as mechanical energy from wind and waves and convection compete with stratification from warming and freshwater fluxes. And it's this conceptual idea of surface force mixing that really sets the foundation for our boundary layer parameterizations. But we also know that this surface forced mixing interacts with a complicated lateral density and flow field. And so, and this is highly variable in space and time. And really the question that, I'm going to rush through these, really the question I'm going to be looking at is how well do the boundary layer parameterizations that are dependent on surface forcing capture all of these fine scale unresolved physics. All right. To do this, I'm using a LES of opportunity that runs from Hamilton et al., about a decade old, and still providing some really nice insight. So this is a large eddy simulation with a resolution small enough to capture boundary layer eddies and large enough to capture this mixed layer instability. So we have a periodic domain with two fronts and a long front wind that creates destabilizing Ekman transport in this unstable region, and a restratifying Ekman transport in the stable region, and a small sliver of space in between the two where nothing is really happening in terms of the frontal dynamics, and we can use that to think of the 1D ocean. And I should say here that this is a kind of a gentle model simulation where the effective heat fluxes of the experimental design were aimed to be about 25 watts per meter squared for the eddies and about 15 watts per meter squared for EBF for the Ekman buoyancy transport. So if you kind of squint your eyes, what you're going to see is that a lot of the action is happening in these baroclinic waves. But if you zoom in, you can see that there's a lot of structure even on the fine scale. And so I took a 400-meter box here. This is, you know, what I consider analogous to maybe a process model such as ROMS or MIT GCM, where you might study some mesoscale dynamics, but are not resolving the boundary layer turbulence. And we can see even within that grid scale that there's a lot of structure. And so we're going to be asking how much does that structure contribute to the boundary layer fluxes. All right, so what we want to do is separate out these fine scale structures from the sub-mesoscale flows. And this is usually done with a bandpass filter. I'm going to be presenting a multi-level Reynolds decomposition, and we're going to see the utility of this in a second. But basically, we're going to divide the flow into an along front mean that is the sum of a sub-mesoscale component, but the sub-mesoscale component is going to be the sum of the mean sub-mesoscale and a turbulence scale, which is going to be the grid scale. And like any sort of filtering, we need a cutoff length. And in this case, it's going to be the transition between 2D and 3D turbulence determined by the Hamilton papers, which is 400 meters. And this is also the scale that Abby Bodner used to, with this model simulation, to identify at what scales we start to get meaningful PV estimates. And so PV estimates above 400 meters resolution, we can start to think of behaving in a way that we expect. And again, we have these three regimes, so we're going to be able to look at this in those regimes. So we can plug this Reynolds decomposition into the buoyancy equation, and we can really nicely begin to isolate the effect of the mean circulation, the sub-mesoscale flows, and the turbulent motions. Or people call this fine scale. I guess I'm going to be interchanging them here. All right, so from this, we generally like to represent the unresolved physics in terms of the mean variables. And so we can do that here with an overturning circulation that represents the along front flows and the eddy flows. And then we're going to use a eddy diffusivity to represent the fine scale. And of course, with any sort of representation, there's going to be some pretty non-negligible horizontal fluxes, but we're really only going to be considering the vertical buoyancy fluxes here, and so we're going to conveniently not talk about them. But you'll notice that, we can, our interpretation of what these overturning flows are kind of depend on where we are, whether we're in the atmosphere and turning these into the TEM equations, or we have an example of this in the ACC, Marshall Radko and Marshall and Spear, where we have the Ekman overturning and the restratifying eddies. And in this case, we too have a Ekman overturning and sub-mesoscale eddies. But in addition to all this, we have this turbulent mixing in the boundary layer. All right, so generally what we want to do is understand what the relative strengths of all of these are, and we can do that using scalings. These are very commonly used scalings to represent these processes based on a combination of theory and idealized modeling. And so we can expect the large scale mean circulation to be scaled with Leaf-Thomas's Ekman buoyancy flux, and the restratifying eddies to scale with Baylor's mixed layer eddy parameterization. And then we might use a boundary layer turbulence parameterization to estimate kappa. And the question is, how well does all this work? And in the unstable region, EBF and MLE work quite well. I'm not going to show them here. In the stable region, EBF begins to deviate a little bit for reasons related to what I'm talking about, although I'm not going to talk about it specifically. What I'm going to be focusing on here is how well this works. All right, so what we're going to do is look at mixing in terms of kappa, which we're going to back out directly from the model in these different regions, and we're going to compare it with kappa that is estimated from different turbulence parameterizations. I didn't label them here, but the outside one is KPP, and the inner ones are EPBL and K epsilon. So all of these are very commonly used parameterizations in a range of models. And we can back out a kappa in the no-front region, and we could see that it works pretty well as any 1D model might expect to work. But if we go to the stable region, we can see that kappa is suppressed. And you might be saying to yourself, oh, well, of course, lateral restratification suppresses mixing, but the results aren't that trivial. And that's because I have already non-dimensionalized kappa here in terms of surface forcing and mixed layer depth. And so this introduces a problem for boundary layer turbulence parameterizations that are based on similarity theory approaches where surface forcing is intrinsic to mixing amplitude and doesn't really know anything about lateral fluxes, and so can't minimize this here. And it suggests that we might be overmixing in the boundary layer in the presence of horizontal flows. All right, things get even more interesting when we go to the unstable region, where we can see that pretty much any evidence of a net down gradient flux has totally disappeared. And we could see that much of this is a result of the more interesting regions, so regions with the strongest gradients, and those regions that have negative PV. We can see that we're getting a down gradient flux. And this is consistent with both destabilizing Ekman transport as well as fine scale overturning. And so these fine scale influences on the buoyancy budget are being captured by our general down gradient approaches. And that's just being shown here. We have integrated kappa that is decreasing in the stable layer and switching sign in the unstable layer. All right. I have no idea how much time I am using up, but that was the main result, but I'm going to kind of be ending on a couple of discussion slides, I guess. So what we're seeing is that the fine scale has a large impact on the buoyancy budget, but the sub-mesoscales really manifest in both the buoyancy budget and in terms of the energetics. And so I'm going to be talking a little bit about dissipation rate here. And we might be able to, we kind of see a consistent story where this is dissipation rate backed out of the model, and the stable region is a little bit suppressed compared to our kind of 1D expected region. And then we see that dissipation rate is enhanced in the unstable region, again, where most of this action is. But these values are quite small. And I'm kind of, but maybe it's not necessarily, okay, so we could see that they change, but they're really only changing by a factor of like 20 to 50% or so. But maybe it's not the average that is interesting, but the statistics that make up this average. And so here I am plotting the data. This is the small scale flux. This is the small scale buoyancy fluxes and the dissipation rate. In the colors on the x-axis, we have the advective terms of the buoyancy of the stratification budget. So this is shear times buoyancy, and we have a PV on the y-axis. And so what we're seeing here is a restratification and on the right-hand side, a negative PV on the lower half, positive PV on the upper half. And we could see that in the no-front region and in the stable region, that the statistics are kind of confined. We might be able to go out into the ocean and be able to measure these and gain those statistics. But in the unstable region, what those numbers are depend on where you are in this regime. And suggests that most of the enhanced countergradient fluxes and enhanced dissipation is happening in this destabilizing transport. But even here, we're, the maximum value that we're really seeing is on the order of 10, for dissipation rates is on the order of 10 to the minus 7 or so. And I was just at a talk by Alex Fisher a couple of weeks ago at APL showing observations of an estuarine front, and they saw local dissipation rate measurements of 10 to the minus 4. So it even suggests here that we're not really capturing all of the energetics. All right, and then that kind of segues nicely into this plot, which shows kind of where this model simulation is in terms of how we observe fronts in the ocean. And we see that it is quite a gentle front where we see much stronger fronts across the oceans. All right, so the results, I guess, are that traditional boundary layer turbulence scalings are modified in the presence of sub-mesoscale fronts. This turbulence is suppressed in regions of lateral restratification, but in the unstable region, we see a lot of fine scale dynamics that actually create a down gradient flux. And these turbulence statistics can vary widely depending on where you are. Okay.
What I think I'll do is we have an open discussion right now, and maybe if I could have our speakers from the morning maybe come up here, and you're able to take questions and comments and things like that. So, sorry, Niklas.
So welcome Lucas and Niklas back up to the stage. And then, yeah, so if anybody has questions in the room, please queue up at the standing mics, and virtual people, please raise your hand using the WebEx raise your hand feature. And I'll keep an eye out for your questions.
Okay, we'll start with Justin Small.
I had a question for Niklas. Good morning, Niklas. Your approach worked very well, and when you tried to fit the convergence with your kind of statistics and your dependence on SST, the residual was quite small. The residual was smaller than your fit, I think, particularly in the peak convergence zone. And I was quite surprised by that. And I was thinking, well, maybe the residuals include the synoptics and atmosphere systems. Do you think some of the atmosphere fronts are within the non-residual, but within your kind of SST fitted part?
For that question.
Please click the button on the mic.
So the approach that I'm taking implicitly makes a scale separation, at least from the conceptual point of view, that are split things into large scale background wind and the mesoscale CCOS temperatures. So an atmospheric front that comes through violates that because it has much smaller scales in the cross-frontal direction, what's comparable with the CCOS temperature. So something is not quite working in this case. However, I think the PDF that I showed you, the joint probability density function of the wind divergence and the gradients of SST, I think in principle, the response that say the wind divergence or the surface winds respond to the SST happens in fronts and in the warm and cold sector in the same way. It's the same physics. It's just modified that this sort of scale separation of my approach doesn't work. So I think the fronts, the synoptic variations in form partly are somewhat captured in the fit, but then there's a large residual as well.
Thank you.
Hello, my name's Peter Solomon. Anyways, just a comment about Leah and Baylor's work. I think the modeling of the ocean boundary layer with a front is actually harder than what they proposed. In my own calculation, we find that when you're close to peak frontogenesis, it's actually the turbulent transport that balances the shear. So that's a really difficult thing to model, and that's my comment.
Do you have any response to it at all?
Yeah, do you agree?
Yeah.
That's my question.
So I think what, if I understand correctly, you're saying that the fine scale transport that we're seeing near the front may not necessarily be representative of the fine scale transport processes.
Yeah, a little bit, but if you look at a classic boundary layer, let's say it's convective, the turbulent transport normally just moves things up and down. But when you actually have a really sharp front horizontally, the turbulent transport actually is the balance for the shear, and it moves things sideways and down at the same time.
Yeah, so maybe I shouldn't be ignoring those horizontal residual fluxes that I put in the residual.
Oh yeah, no, I'm not throwing rocks at you or anything. It's just a comment.
Excellent, thank you.
So my question, surprise, is about stress. That's probably wasn't a good move. Stay. And it could go to Larry, actually, or Niklas, I think. So use of scatterometry, of course, we often relate the backscatter to stress more than wind. Well, we do all sorts of things to get the magnitude of the wind right from scatterometry. That's great. But still, the direction of the wind is more the direction of the stress vector than the wind vector at the surface. So besides the fact that its stress is proportional wind speed squared, and I was more interested in looking at effectively the stress vector when you're looking at your divergence terms and the curl and all those. Does that have any impact on your elegant analysis, which I love, but I was just curious. If you were to consider the wind the stress, would you get vastly different results, or do you think they'd be about the same? Oh.
Jesus. Okay. Oh, I see. Okay. So I don't think you would get vastly different results with the stress. Simply based on the argument that the perturbations that we have due to SST are typically much smaller than mean winds. So the stress and the mean winds are simply a Taylor expansion between the two, and it's simply I look at the linear term. However, the stress, of course, is also influenced by ocean currents, ocean waves, and the like, which are not captured by the SST effect that I have right now. So there's something I've actually played with that, where you do this approach, this impulse response to function approach, and now do it with two variables. Rather than just SST, you also do sea level as some kind of proxy for geostrophic flow. And then you get two impulse response function, one for the SST and one for the ocean currents, all based on equivalent neutral winds. Right, that's what observations are. But still, there is some signal. But so there is an aspect of that where that could be extended to look into the current effect in some, again, within the limitations of the equivalent neutral wind measurements, that impact can be put in. It would be very interesting to see if, let's say, for ocean waves, if you put that in there, if we do this analysis, I condition it by the large-scale winds, direction, and speed. You can also condition it by some kind of measure for the direction or the age of the waves, for old waves, young waves, this sort of thing, and seeing whether you get any different results. I mean, there's endless things you can play with this in terms of conditioning the regressions. Ultimately, it's just a matter of having enough data. I mean, this is, as you see, the signal to noise is very poor, and the more conditions you put in, the harder it is to get anything reasonable out of this whole analysis.
I'm Elizabeth Thompson from NOAA. I have a question for all three of you about, for the unresolved physics or the subgrid scale or the nonlinear dynamics, how would you suggest, like, what do we need to observe or constrain? How would we go about doing that for the hope of improving predictions?
Yeah, I guess my last slide of showing the turbulence statistics was kind of foreshadowing maybe the conversations that we'll be having later on this week with the observational challenges. I mean, TKE dissipation rate is something that's being more readily observed in the oceans, and so we might be able to start to constrain statistics. Moving forward, vertical buoyancy fluxes, of course, are much more difficult to constrain in the upper ocean, but being able to look at specific regions and the averages across them is kind of where we want to head, I would argue.
And I think just putting a plug for the new satellite observations that are being discussed. Again, I'm basing this analysis on observations of sea surface temperature and equivalent neutral winds from satellite. I think, again, as it's discussed now, putting in ocean currents would basically start to resolve the double Ekman layer, and I think it will open up an enormous opportunity, a window to both exploring new dynamics and sharpening the ones that we have. All that, of course, would require in situ validations. And so there's not just the satellite aspect that would have to be done, but also an ocean-going in situ part of this observational strategy.
And I'll just mention here too that there's kind of a theme in some of the talks this morning on spatial scale. So as we go from larger scales and start going to smaller scales, so what we call the mesoscale is something on the order of about 10 kilometers to maybe 500 or so. But when you start going smaller than that, we start seeing these very different things. Leah showed a very good example of some things we do, and so the fluxes are much stronger, and the air-sea coupling is much different. So this is a really important question that we're trying to get a handle at right now: is what are we needing to observe? So it's a really good question.
Thank you, Larry. That's a good segue for what a question I wanted to ask Laurindo. Lucas, thanks for the review and your talk. The mechanisms that you discussed for the coupling, how dependent are they? Are they independent of the latitude? So if you go from equatorial to tropics to exotropics and mid-latitudes, how do those change? And that's sort of a secondary question to Leah on her analysis of how that would change as we go up in latitude. So not just scales, but also as a function of F.
The analysis that I've done based on the spatial scale was just did not try to constrain by the physics, just was data analysis. And what it showed when I computed those relationships as a function of latitude, it showed latitudinal dependence on the transition scale between the part of the spectrum that's dominated by the atmosphere and the part that is dominated by the ocean. The transition coincided with the atmospheric rust radius of the formation. For reasons that are still not very clear, I think it's because just the shape of the atmosphere of the spectrum of internal atmospheric motions depends on the rust radius of the formation, like the part of the spectrum that starts to decrease towards, where the variance starts to decrease towards higher wave numbers. And we can also see some dependency on the transfer functions, like what Niklas was talking about, like the amount of change in the near surface winds by SST. There's also a latitudinal dependence on that, but might be related to the intensity of the background winds. Winds are much stronger in the Southern Ocean, but I'm speculating. I have not peered deeper into that.
Yeah, going along with speculation because I don't know. So at higher, it's really this, there's going to be both a competition between time scales and space scales. So at higher latitudes, of course, everything happens much faster, but is also going to be much smaller, whereas at lower latitudes, you might have larger scale, sub-mesoscale features that evolve on slower time scales. And, I will note that, this is constant wind forcing over 10 days. And at day 10 was when we were looking at these model simulations, but we never see constant wind forcing or surface forcing on over 10 days. And so, yeah, those nonlinear actions matter.
Maybe just one quick comment on this. I mean, just in terms of latitude dependence, of course, the results, these impulse response function that I showed you, they depend on F. And so if you go to the southern hemisphere, symmetry is the other way around. I mean, it's now it's on the left versus on the right. I mean, so there's very simple, there's obviously F scaling with Coriolis in there, which also informs the scaling of the Rossby number versus a comparison of time scales between the vertical mixing and advection. As compared to F versus advection, so you might shift from a really irrotational system to one that's affected by rotation as a function of latitude.
Hi, my name is Sikar. I'm from University of Rochester. I have a question to Dr. Schneider. I have seen so many papers that talk about the crosswind and alongwind sea surface temperature gradients and talking about call and divergence. I was wondering why we just use the divergence instead of using the full strain tensor, because I think divergence is just a trace of the tensor. And instead of just using a long wind SST gradient, why not use the full gradient and look into the whole tensor and that gradient? What's the advantage of just using the divergence?
And I think it's maybe a historic and geophysical reasons that the surface wind divergence and curl have obvious relevance for the circulation both in the ocean and the atmosphere. But you're absolutely correct. When you basically do a reconstruction or fit, ultimately you want the winds, and taking a gradient operator of the winds is a very convenient way of focusing on the higher wave numbers. But you're absolutely correct. If you think of these coupling coefficients that I showed or that have been published in many, many papers that look at the divergence and curl, as this one paper that Lucas cited, Moreno, where he looks now and saying, okay, the divergence part of the wind is typically, if you invoke the pressure gradient, the pressure mechanisms is related to the Laplacian of the sea level pressure. But you would say, well, maybe if you look at the momentum equation itself, maybe it's not so much the whole Laplacian, but it's simply the crosswind momentum equation that's important, which would give you a relationship between the crosswind divergence or slope of the crosswind component of the wind response versus the curvature in the crosswind direction. So that's exactly what you're suggesting, is that rather than look at divergence and the curl, simply look all the gradients of the velocity field in the coordinate system aligned and perpendicular to the large scale winds, and look at, of each component, look at the relationship with the various aspects of sea surface temperature. Thank you.
Okay, we'll do Stuart, and I think we're probably at the break, right? Yeah, cool.
Hi, this is Stu Bishop from NC State. I had a question for Niklas. So I was thinking, when I look at these divergence maps, I think of vertical velocity. And so really the communication between the boundary layer and the free atmosphere is really the top of the boundary layer. So you got to integrate the continuity equation. So how important, I mean, maybe it's a plug for more observations in the atmospheric boundary layer, but how important are things like the boundary layer height? Because I would imagine that changes as you cross the Gulf Stream.
Of course, with this analysis, I can't do that. I mean, I only have the surface observations, but you're absolutely correct. I mean, this is sort of a key aspect, because the surface wind divergence I see in large part might be simply overturning in the boundary layer. Right? Something like a sea breeze overturning in the boundary layer, so nothing really that couples, but a part of it might go out. So absolutely, I think numerical models, analysis of the vertical structure, Justin Small is looking at atmospheric models where you look at the vertical structure. I think that's a key thing to do, and that goes beyond that. From observations, a little bit tougher to do that, but if we have the observations, maybe you can try it. But if you can try to find the observations either in a particular experimental settings and do that. But I think the vertical structure of the response and how it either enhances or how it damps out away within or away from the boundary layer is a key question. Whether this is just sort of interesting boundary layer dynamics or it's really relevant for the large scale flow. That's a key question.
Thank you.
Cool. All right. Well, let's thank our speakers once again. I think we're going on to a break now. And then we'll reconvene at 10:10.
Right. So Hisashi Nakamura will be talking to us about an overview of climate impacts on mid-latitude ocean fronts and eddies.
Hi, I'm Hisashi Nakamura from ArtCast, University of Tokyo. First of all, I'd like to thank the organizers, namely the US CLIVAR Ocean Mesoscale Air-Sea Interaction Working Group, for offering me this opportunity to give an overview talk. I wish I could join the meeting in person, but unfortunately I cannot. I considered making an online presentation, but it's now 2 o'clock at night in Tokyo, so I decided to record my presentation. Let me start my presentation with reminding you of the complex nature of extratropical air-sea interaction characterized by the hierarchy of multi-scale processes and phenomena, as illustrated in this nice schematic taken from the brand new review paper by the US CLIVAR Working Group. The interaction involves many processes from the upper ocean up into the free atmosphere through the ocean mixed layer and atmospheric boundary layer. Due to the time limitation, I cannot fully cover the whole processes, so I focus mainly on free tropospheric responses to mid-latitude ocean fronts and eddies, featuring their climatic impacts. I would like to point out that the positive local correlation between SST and upward surface heat fluxes can be a measure of ocean thermodynamic forcing on the atmosphere. As shown in the left figure, a recent semi-observation flux data indicates the positive correlation along the narrow western boundary currents and associated mid-latitude SST fronts, which is well reproduced in the high-resolution coupled GCM, but not in its lower-resolution version. The mid-latitude ocean had been believed to be passive to atmospheric forcing until high-resolution satellite data and numerical simulation became available in recent years. Before discussing free tropospheric impact, I quickly look at a boundary layer response to an SST front to find a connection to discussion in the first morning session. As indicated in the top panel, a steady response of surface winds to an SST front that forms between warm and cool ocean currents depends strongly on the wind direction relative to the frontal orientation. As in the right panel, winds undergo rapid acceleration in crossing the SST front to its warmer side. This is because enhanced heat supply from the warm current destabilizes the boundary layer, and thus downward transport of wind momentum by turbulence is also enhanced. Through this vertical mixing mechanism, surface winds are divergent around the SST front. As in the left panel, if winds are parallel to the front, the warm SST effectively heats the overlying atmosphere to lower the surface pressure, thus causing surface wind convergence and ascent aloft. This is called pressure adjustment mechanism. As a typical example, I present composited surface wind convergence and divergence in the KOE region under the enhanced winter monsoon based upon the reanalysis data with high-resolution SST. The Oyashio front extends northeastward, east of Japan, and the cold monsoonal northwesterlies are crossing this front. The vertical mixing mechanism is operated to yield surface divergence. By contrast, another SST front along the warm Kuroshio extension is more parallel to the monsoonal winds, and thus favorable for the pressure adjustment mechanism. As a result, surface pressure is lowered to form a pressure trough, thereby yielding surface convergence along the extension. In combination with abundant heat and moisture supply from the extension, the surface convergence helps organize shallow convective precipitation. The latent heat release and heat supply from the Kuroshio extension both promote frontogenesis, thereby reinforcing the convergence. As shown in the right panels, climatological surface wind convergence and rain bands are also observed along the Gulf Stream. Thus, some modifications are required to the schematic by incorporating the enhanced moisture supply from the warm current and the formation of a convective system, which is partially a free tropospheric response. As discussed later, a major storm track forms along the SST front along the Gulf Stream. Therefore, the climatological mean surface convergence and air-center loft, as well as the precipitation band along the Gulf Stream and in the left panel, cannot be interpreted without incorporating contributions from migratory cyclones and associated fronts. The middle panel shows a snapshot of satellite image. The moving image suggests the organization of a band of developing convective clouds along the Gulf Stream under the cold westerlies behind the developed cyclone. In such a case, the SST front is also favorable for atmospheric fronts to be enhanced or stagnated. The accumulated contribution from those events are considered to account for the major fraction of the time mean features. As shown in the lower panel, the major storm tracks in the wintertime northern hemisphere form climatologically on the major SST frontal zones along the Gulf Stream and the Kuroshio-Uyashio extension. This is because differential heat supply across the SST fronts efficiently restores near-surface programmicity, allowing recurrent development of migratory cyclones and anticyclones. This is also because abundant heat and moisture supply from those warm currents is favorable for cyclone development. And in the top panel, transient disturbances developing along the storm tracks exert feedback forcing on planetary waves to maintain strong surface westerlies over the mid-latitude ocean, thereby driving the westerly boundary currents. Let's take a closer look at the atmospheric response to the SST front along the Gulf Stream. O'Reilly et al. Compared 50-kilometer AGCM simulations with the realistic SST front and smoothed SST gradient. The upper panels show their climatological differences. The SST front enhances climatological storm track activity indicated as stronger poleward eddy heat flux in the middle panel. As shown in the upper right panel, energized transient eddies maintain the eddy-driven North Atlantic jet by enhancing eddy momentum flux convergence. Therefore, likelihood of northeastward jet deflection increases just like in the positive NAO, as in the lower right panel. The enhanced storm track activity also maintains a planetary wave ridge over Europe, leading to a significant increase in blocking high events closer to the observed frequency. Their results suggest that realistic representation of Gulf Stream front in high-resolution climate models can lead to better representation of atmospheric mean state and variability, as confirmed by Primavera high-res MIP project. Likewise, climatological impact of frontal SST gradients and the western North Pacific on the atmosphere can be extracted from AGCM simulations. The SST front in the KOE region climatologically enhances storm track activity in winter, and energized transient eddies acts to reinforce the eddy-driven jet through enhanced momentum flux convergence, as indicated with diverging E vectors, with increased likelihood of poleward jet deflection downstream. Compared to its Atlantic counterpart, the tropospheric response to the Pacific SST front more effectively strengthened upward propagation of planetary waves, thereby acting to weaken the polar night jet and cold polar vortex in the Arctic stratosphere. Compared to its northern hemisphere counterpart, mid-latitude SST front is more zonally extended over the southern hemisphere, with its core region along the Agulhas return current, collocated with the storm track core and rain band. AGCM simulations suggest that SST front acts to enhance storm track activity and thereby maintain deep eddy-driven westerly jet around 50 degrees south, making the Southern Ocean stormy. The AGCM simulations also suggest that SST front may be essential for realistically reproducing the southern annular mode at the wobbling of the eddy-driven jet, as well as the balconic annular mode at the hemispheric pulsing of storm track activity. I now discuss the atmospheric response to persistent SST anomalies due to ocean front variability in the KOE region, which may be a key for the PDO. Statistical analysis have found that warm SST anomalies due to the poleward shift of the subarctic front or a Kuroshio extension front locally enhance heat and moisture supply, which tend to induce an anticyclonic response downstream by modulating storm track activity. The tropospheric response to the Pacific SST anomalies can modulate upward propagation of planetary waves, and thus the influence reaches the Arctic stratosphere. Interestingly, the tropospheric response to cool SST anomalies due to equatorward shift of the Kuroshio extension front is found weaker and not symmetric to its counterpart to the warm SST anomalies. Similar nonlinear features are found also in the atmospheric response to the meridional shift of the Gulf Stream. As discussed earlier, decadal scale poleward shift of the subarctic SST front in the KOE region tend to induce a PNL-like anticyclonic response with poleward deflected storm track activity. As shown in the upper panels, a quarter-degree model simulation by Smirnov et al. Can reproduce this response because transient eddies along the poleward shifted storm track are well reproduced. As in the lower panels, however, its 1-degree version cannot, because near-surface anomalous heating accompanies unrealistically the cold anomalous northerlies. These results are consistent with recent studies showing particular importance of high-resolution models in reproducing moist processes in developing cyclones. A statistical analysis by Willis and Thompson suggests that atmospheric anomalies regarded as a response to time-varying SST in the KOE region can differ fundamentally from those that forced the SST anomalies. The forcing atmospheric pattern shown in the left panel is highly significant, but the atmospheric response in the right panel is less significant and looks similar to the low-resolution model response by Smirnov et al. Essentially the same results are obtained from coupled model simulations, and a similar response is also found to time-varying SST along the Gulf Stream. I'd like to point out that those time-varying SST anomalies may not necessarily be associated with SST front variability caused by oceanic processes. the latter should cause more persistent SST anomalies. Those two types of SST anomalies with different persistence may lead to fundamentally different response in the atmosphere. I now move into large-scale atmospheric response to mesoscale SST patterns, which has been studied basically through numerical simulations. Ma et al. Attempted to extract atmospheric response to meso-frontal-scale SST pattern in the KOE region, as in the left panel. They conducted a time slice simulation for a particular cold season with 27-kilometer regional model with high-resolution SST, and then compared it with its counterpart with spatially smoothed SST. Warm mesoscale eddies are found to increase heat and moisture supply into the atmosphere, which acts as a thermal damping for those eddies, but as thermodynamic forcing on the atmosphere. The enhanced heat and moisture supply contribute to cyclone development, thereby intensifying storm track activity across the basin and thus acting to displace the eddy-driven westerly jet poleward over the eastern Pacific. Those processes, however, cannot be reproduced in the model with substantially lower resolution. Next, I'm introducing an idealized model experiment by Fassard et al., which is instrumental in understanding atmospheric responses to mesoscale SST patterns. An 18-kilometer regional atmospheric model is configured into a mid-latitude beta plane channel. A zonally symmetric SST with a front in the middle of the channel is prescribed for the control simulation. Then, mesoscale eddies are randomly added to the SST field for the eddy simulation, as in the middle panels. In the eddy simulation, heat supply is locally enhanced from warm eddies, and so is precipitation under the cold airflow behind the cyclone. Zonal mean statistics shown in the left panel suggest that enhancement of the heat and moisture supply from warm eddies peaks on the warmer flank of the SST front, where eddy SST magnitude is set particularly high, and climatological storm track activity is also high. And in the second panel, an increase in convective rainfall maximizes further south, corresponding to deep diabatic heating response in the third panel. As shown in the upper right panels, modulated mean meridional circulation by increased convective rainfall and increased stratiform rainfall both acts to warm up on the cooler flank of the SST front, leading to poleward shift of the storm track and eddy-driven westerly jet. These results are consistent with those by Ma et al. I'm finishing my talk, leaving many topics untouched, as listed below. For example, specific air-sea interaction processes involved in extratropical cyclone development, including a role of warm and cool conveyor belts, cannot be discussed, nor the oceanic contributions to moist processes involved in blocking formation. I should have discussed the dependence of model reproducibility of atmospheric responses to frontal SST anomalies upon model biases through preferred modes of variability, and also its model resolution dependence. We need deeper understanding of the dependence of atmospheric responses to frontal SST anomalies on how they have formed, if through ocean processes or atmospheric forcing. I didn't have time to discuss interbasin covariability of the Northern Hemisphere western boundary currents and the influence of their rapid warming on extreme rainfall events, in addition to rows of mid-latitude air-sea interactions in the projected future climate. Finally, I would like to point out that assessing relative impacts between ocean eddies and SST fronts on the atmosphere can be technically difficult in realistic situations, and the separation SST field might be possible by focusing on flow curvature. Thank you for listening to my talk. I put relevant review papers here for your reference. Enjoy the rest of the meeting. Thank you again.
Okay, I think we can move on to the next presentation, and then we'll have again 20-minute open discussion session at the end of the session. Okay, next speaker will be Thomas Spengler from University of Bergen, diabatic effect in the evolution of cyclones and storm tracks with western boundary currents.
Hi. Good morning, everyone. It's great to be here. So I didn't do this work all alone, so there's a lot of co-authors here, but I will also mention them along the way. So I'm an atmospheric person, and I'm mainly focused on synoptic scale, that was mentioned earlier as well. And so they will be mainly focusing on what's happening in the atmosphere, but motivated by what the ocean provides. So this is no surprise for anyone in this room here. So this is basically sensible and latent heat fluxes. They concentrate along the western boundary currents together with their variability, actually. And the interesting part is, if you want to understand how this impacts the atmosphere, is like which scales are of relevance. And so we talked a lot about scales earlier. This is just an interesting analysis we tried here, where often in climatologic context use monthly means. That's the bottom right figure. And that will be the wind direction associated with all fluxes. So we will basically see it's westerly flow, whereas if you actually use 6-hourly data, you see it's very much eddy dominated, what determines the fluxes. And therefore also the relevance of these cyclones on the synoptic scale that we heard about earlier becomes very evident when you want to dynamically understand what's going on there. So, is this working? I can't advance the slide. Ah, now it's coming. Okay, so if you want to understand the cyclones, what we do in micro very often is we detect features. The features could be a cyclone, which is there depicted on the left, and then we can track it in time in a reanalysis data. And we can also detect SST fronts in the ocean. And then basically what we tried here, we tried to understand, is there a significant difference between cyclones crossing the SST front in specific ways? So you see it on the right-hand side. So if this is like a typical situation, it's SST front, and then you have cyclones crossing from cold to warm or warm to cold, or they stay only on the cold side or on the warm side. And then the question is, do these cyclones behave significantly different? And what we looked at in this case is how strongly they intensify. And so what you see is that on the Gulf Stream, it's mainly these C3s. These C3 is the ones coming from the warm to the cold side. They intensify most rapidly. And actually, if you look on the right-hand side, this is distance to the SST front with respect to the time when they intensify the most. So you see that these cyclones, also in the Kuroshio, actually intensify the most just when they cross the SST front. But that could, of course, be cause and effect, right? So it could also mean once you cross the SST front, you can't intensify as strongly anymore. Hence, your strongest intensification was before. So this raised more questions and it helped us answer things. But we did the same analysis for, and now it doesn't work again. Do I have to point a specific direction? So then we did this also for a simulation that was provided by Japanese colleagues with the atmosphere's global circulation model with different SSTs, control and smooth. And again, we tracked the cyclones, we detected the SST front, and we did the same analysis. And interestingly, and to our surprise, there was no difference. So the cyclones themselves individually, they do not care about the intensity or the strength of the front, which was very counterintuitive to us. So then if you fail with observations or reanalysis, maybe it's time to go back to theory. So that's what we tried then. So we used the ED model, which is like a standard model for assessing baroclinic instability. And we added surface flux or effects of surface fluxes and also latent heat release in the free troposphere on the development, and tried to then turn a lot of knobs to understand what surface fluxes or latent heat release will do to the storm. And so what we did is we had this development, and then we put the surface sensible heat fluxes at different positions into the cyclone, and just to see what that does. And in general, it's detrimental. So, for example, if you have a cyclone, the cold sector is usually heated and the warm sector is cooled by surface fluxes. So that's detrimental to baroclinic development. However, what we found is all of this detrimental part can be very easily overcome if you allow latent heat fluxes to have an indirect effect. Here you go. And that basically, if you release latent heat in the free troposphere because you had added moisture from the ocean surface, then all this surface sensible heat flux influence on the cyclone you can just forget about. It's tiny, it's marginal. So we coined this the direct and the indirect effect, and the direct being detrimental but very small, and the indirect is the supply of latent heat from the ocean that will fuel the cyclone development. So then, of course, you can say this is a very idealized model. How would that look like in a more complex situation? So what we did is we did a simulation with WRF, where we initialized on the left-hand side as a jet stream, so it's a typical mid-latitude baroclinic setup, and we developed a cyclone in it. There's moisture and there's surface fluxes. And basically what we then tried to figure out is to reconcile what I showed earlier, that the front or the intensity of this front doesn't matter so much, and that maybe the latent heating associated with the SST is what's really mattering most for the cyclone. So we ran a lot of different SST, which is the middle fit panels. So we had same SST gradient, but different absolute values of SST. So we made it warmer or colder. We had the SST gradient change in intensity. So we made it very sharp transition from warm to cold or very relaxed. Or we moved the SST front a bit poleward or equatorward with respect to where the baroclinic zone in the atmosphere was, and thereby where the cyclone develops. And then we investigated the heck out of these simulations, and at the beginning we couldn't really make much sense of it until Hai Bui, the postdoc who published this work, then also said, okay, let's take a step back and let's just look at what fuels the cyclone. The cyclone is fueled by the latent heat. Where does the latent heat come from? It comes from ahead of the cyclone. It's because the cyclone moves eastward and then sucks in this moist air. And then this moisture loading there is basically Clausius-Clapeyron related to the SST underneath. So then basically on the right-hand side, you see that no matter what you do with the front or where the front is or how strong it is, it's mainly the SST downstream that influences the airstream that feeds the cyclone, which is illustrated on the next slide. I get there? Yeah, so this is basically what I just said. And then one more, here we go. So there's a cartoon illustrating this. So there's the cyclone. And then the red stream is the stream what ends up what we call in the atmosphere the warm conveyor belt. So it's basically what's fueling the latent heat release in your storm. And basically on the top one, you see this red square. So that's basically where the moisture loading comes from that 24 hours later will end up fueling your cyclone. So that's also then not too surprising if the cyclone is most sensitive to the latent heat release in the cyclone, that this feeder airstream is actually where it gets the moisture from is the most essential part. There's of course all this action in terms of surface interaction with the ocean and the cold sector, but the actual cyclone, this individual cyclone here, doesn't see that so much. It affects mainly the boundary layer and the next cyclone by loading the moisture into that area. But the individual cyclone is mainly influenced by this indirect effect, surface fluxes, which basically determines how much moisture I can use in my cyclone and thereby intensify it. So this was basically tying them together why the SST front strength might not matter so much, but the SST themselves. Okay. Here we go. So then if the individual cyclone cares mostly about the latent heating, then we tried to integrate that up to understand the storm track. And I'm not going into all the details, but basically baroclinicity means how steep is an isentropic surface in the atmosphere. So what we did is we developed a diagnostic that tells you how steep it is and why is the steepness, the slope, changing due to either diabatic effects, which can be from the surface fluxes, that's the red arrow, or from latent heat release in the free troposphere. The heating, no matter if it's sensible surface heating or latent heat release, will always intensify the baroclinicity or the slope. Whereas you have mass rearrangements due to baroclinic instability, for example, that will reduce the slope. That's basically a conversion of available potential energy into kinetic energy. So when you then look at how this behaves in the storm track regions, so we have done this for the Gulf Stream and the Kuroshio regions. So you can basically look at how does this slope, so the baroclinicity change in time, and how does this hang together with the diabatic forcing versus the tilting. And then actually we found something very interesting on the right-hand side is that the upper and the lower atmosphere behave very differently. So the lower atmosphere is very much cold air outbreak driven, meaning a cold air outbreak means you have kind of a cold phase and the cold air wants to run out. So you have a lot of tilting trying to swash out the cold air. And then the surface sensible heat fluxes will try to push that isentropic surface back. So basically it's difficult to point for the online people, but so in the lower part it's basically 1, 2, 3, 4. So basically first you tilt and then you heat back to your original state, and then we went through a cycle of baroclinic intensification and weakening. In the upper atmosphere is actually the opposite. So then the cycle goes this way, and basically means first you have latent heat release, intensifying your baroclinicity, and then the cyclone can use it and increase eddy kinetic energy. So it's very different if you want to understand the influence, the direct influence of the ocean on the lower atmosphere, or the indirect, as I call it, on the free troposphere. And this has to do with, if you look at this phase when the diabatic heating in the free troposphere is most relevant, it's basically how much moisture loading can you provide into the storm track. So bringing it back to the ocean then, if it's all about the moisture loading, what Fumiaki and I did, we looked at some simulations with an aquaplanet, basically, where we prescribe different SSTs. So we have an SST front and you move it at different latitudes. And you look at the water cycle, because ultimately what I'm arguing for is that it seems like the storm track cares most about, as we also heard from Hisashi now, about the latent heating and the water cycle. So when you move the SST front, you basically move the water cycle where the evaporation occurs and where the precipitation occurs, which is on the right-hand side, right? So red is evaporation, is kind of limited by the SST front sits, and then you have the precipitation, which is large scale in particular that I'm talking about in the storm track that falls just poleward of that front. And then if you're interested in the intensity of this storm track, you can look at what is the diabatic part contributing to my eddy available potential energy. And basically what you see here, red is the front at 35, black is at 45, blue at 55. So basically you move that heating pattern with your front. But as you move it poleward, the colder it is, the less water loading you can have, Clausius-Clapeyron, hence the less diabatic intensification. But of course, you can easily fix that if you just make the ocean warmer or colder. So basically, you can reinvigorate your water cycle by having higher or lower SST. So this is a very strong indication that it's actually the SST itself that really determines the water cycle and thereby the intensity of the storm track. And then the positioning of the front basically tells you where all this action then actually occurs, where the water loading comes from, basically. All right. So with that, I wrap up. So I showed you that these exotropical cyclones, they're mainly intensity-wise influenced to this indirect effect, so through latent heating. And that mainly comes from the SST downstream, so you can directly relate that. Then I didn't show that, but what's interesting, of course, when you have the smooth and the sharp SST front, as I told you that the individual cyclone doesn't care so much, but the climatology is very different, as we all know. Interestingly, what we did an attribution, and we found that most of the difference in terms of precipitation and surface fluxes does not co-occur where the cyclones are. So it depends on colder outbreaks, for example. Then, as I showed you, the diabatics play a key role for the storm track position and intensity, and thereby directly relate to the SST and the water cycle associated with that. And all of this is pointing also to the importance of these, what we discuss here, these sub-weekly synoptic scale interactions, basically. I'll leave it there. Thank you.
Proceed with the next talk, and then lead the question for the next one. So next presentation will be done by Xiaoqi Wang from Texas A&M University. Impacts of mesoscale SST variability on SST variability in rainfall variability.
Hello everyone, it's my pleasure to talk here. So my name is Xiaoqi Wang. I'm a PhD student from Texas A&M University. My supervisor is Dr. Ping Chang. Today I would like to talking about the impact of mesoscale SST variability on rainfall variability. So why we care about mesoscale SST variability? Here is a snapshot of SSH global map from Charlton. So we can see there are many mesoscale eddies along the ocean fronts. So it has already been demonstrated that the mesoscale SST variability forcing can have an impact on the planetary boundary layer, while driving a response of near surface wind and the turbulent heat flux. For example, as we are familiar with this Spengler's paper, so they suggest that the mesoscale eddies will have the atmospheric imprints by using the composite analysis, and then they put forward a schematic. So for example, as for the anticyclone, the atmosphere pressure adjustment to the local SST sharp gradient will raise up cloud top height and then increasing the clouds convection and rainfall. But however, they are talking limited within the boundary layer. So then I have think about these two interesting questions. So first one, whether and how the upper troposphere responds to the mesoscale SST variability forcing. And the second question is, to what extent can our high-resolution climate models realistically simulate precipitation response to this mesoscale SST forcing? The data sets I used in my study, including both the observation reanalysis and also as well as model simulation. For the observed precipitation, I'm using the GPM trim, and also for the using the OIST and the global color model, the satellite data for the total cloud fraction, and for reanalysis data, here I'm using the EI file. As for the model simulations, we are using the CESM version 1.3. So it is the sandwich transient range coupled high resolution with a nominal 1/4 degree, and also a coupled low resolution with a nominal 1 degree. So it is including the period from the 1950 to 2100, including the historical runs and the future prediction. So about the models, more details and the data set are available on this website. First of all, I want to mention that all the data sets are regraded to a nominal 1 degree uniformly with the mass conservation. And I'm using a spatial filter 1 by 1 degree two-dimensional moving average. It is to separate the mesoscale variability from the large scale. So here we will take a look first at the observations. This map shows the ST variability at the different scales. So it is for the total ST variance at the top, and the middle will show high pass filter, which is the small scale ST variance, and the bottom will show the large scale ST variance. To show these signals more clearly, here I will turn to a ratio map. So figure B will show the small scale ST variance over the total one. And we can see all the western boundary currents region, more ST variability is controlled by the small scale processes, which is like the mesoscale oceanic eddies and the meanders. But at the trops, we can see at the figure C, it is the large scale ST variance over the total one. We will see at the trops, the large scale variance dominates as we expect. So since they are different at the different scales, so how about the atmosphere response to this ST forcing? Here we will see the left panel is a correlation map between precipitation and the ST. The right panel will show the total cloud fraction response to this ST difference. In the middle, it will show in the at the small scale. So we will see the imprints of the mesoscale ST forcing on both the precipitation and the total cloud fraction. So it may suggest think about the mesoscale ST forcing. It may impact on the upper troposphere, not only limited on the boundary layer. So then how about our model simulation? Here are the snapshots of the small scale SST and the precipitation anomalies. at the top, so it is come from the coupled high resolution. We will see there are remarkable mesoscale signals over these frontal regions, but in the low resolution at the bottom, we cannot see them. So since they are so different in the high resolution and the low resolution, here we want to see how the atmosphere responds different. So the left part shows the coupled high resolution correlation map, also between the precipitation and ST. Right panel will show the coupled low resolution. So since we first focused on the small scale, so we will see the big difference shows up over these eddy-rich regions. So we will see there is a relatively remarkable and significant precipitation response over these frontal regions, but we cannot see these signals in the coupled low-resolution simulations. And also, since we have already seen the precipitation cloud fraction response, we will also wondering how the omega will show the different way. So here I will using the two levels. So left part will showing the omega at 850 h-pa. Right panel will show the omega at 500 h-pa. So all these are focused on the high pass filter, which means small scale. So we will see over these frontal regions, the small scale SC forcing can have a deep reaching effect on the upper troposphere in both ERA5 and coupled high resolution. But in the coupled low resolution, we cannot see this process. So to see the vertical structure of omega in details, here I'm trying to use a composite analysis to take a look. So the key point is how to define these events. So here I'm trying to use a wavelet coherence transform. So first step is to choose the focus region. So this is based on the left figure. So it is a high pass filter correlation map between precipitation and SST. Then I will choosing the Gulf Stream region from the 45 to 70 western longitude and 40 north latitude. So after removing all the climatology and using the spatial filtered SST and precipitation, I did the wavelet coherence at each grid point. Here is an example at the right panel. So since we can see almost the stronger and the significant coherence occurs below 1 year. So here I will choose to scale average the power between 2 and 12 months, which is also past the significance. Then finally, I will call it as warm events. So that means the coherence is larger than mean values plus 1 standard deviation, and also the ST anomaly should be positive, which means it is induced by the warm eddies. So here we go to the composite results. So it shows the vertical structure of omega based on the composite analysis. So the positive values means upward motion. We will see in the coupled low resolution, we can now see the stronger signals, but in the coupled high resolution in the middle and the ERA5 at the right, we will see there is a relatively stronger omega response to this small scale ST variability forcing. And these signals will be more clear in this mean state at the left. So these lines, the blue lines will show the coupled low resolution, which is almost remains stable. But the red lines coupled high resolution and black lines ERA5, we can see there is a stronger response. And this can even extend up to the 700 h-pa, which is also consistent with our previous results. So all these signals may suggest that local ascending motion induced by the warm mesoscale SC forcing can extend up to the middle or even upper troposphere in both CESM coupled high resolution and ERA5, which enhances the convective precipitation, but it lost in the coupled low resolution. And also the same thing happened in the crucial extension region. I using the same composite analysis and doing these composite results. So here we also still cannot see any signals in the low resolution, but it shows up in the high resolution and EIA file. So finally, I hope to give a short summary. Based on the observations and the reanalysis, we found that small-scale ST variability dominates at the frontal regions, and the imprint of mesoscale ST forcing on the vertical properties and the precipitation is not only on the atmosphere boundary layer, but also the upper troposphere. And as for the CESM simulations, we found that the coupled high resolution can produce a precipitation response to the mesoscale ST variability forcing that is consistent with the observations and EIA file. In contrast, low resolution simulations fail to capture such a response. So since they lost the mesoscale ST variability. So I think that's all for today. Thanks.
You can sit here and we can have a open discussion. Hisashi won't be here, but maybe Justin can sit there together and then contribute to the discussion. Again, if you have any questions to the speakers, please come to the microphone and ask your questions. We do have one question from WebEx. I think I lost it. Sam, can you read the questions?
Yes.
From Yolanda? Yeah.
A question from Yolanda Sarah for Thomas. And if you want to unmute and ask yourself, you can certainly do that. But yeah, so in the chat, they wrote, did you compare impacts of SST versus upper ocean heat content? Is SST all you need to measure, or would information about the upper ocean temperature also be helpful?
Yeah, and I can elaborate. I'm here.
Yes. Thanks for the question. So we did not look at ocean heat content. So for all the simulations I showed, there was no, sorry to the oceanographers, there was no real ocean, right? So it's just SST prescribed, right? So I guess what you're trying to get at is like if there is a continuous interaction, would there be a feedback in terms of, if you suck out the heat from the mixed layer, or I mean, alternatively, you can also maybe you punch further down into other layers where you can extract more heat, but we did not look into that, no.
Okay, thank you.
Elizabeth.
Hi, Elizabeth Thompson, NOAA. I had a question for the last speaker about your high resolution versus low resolution. Did you, was the whole model higher resolution, or was it just the SST that was higher resolution?
It is a whole low resolution model. So for the atmospheric part, it is follows the resolution is a nominal 1 degree. Yeah.
Clarify that, Elizabeth. High resolution.
Turn the microphone.
Touch that. The high resolution was 1/10 degree in the ocean and 1/4 degree in the atmosphere. The low resolution was about 1 degree in both ocean and atmosphere.
It was just very striking, the difference in the free tropospheric response. So I was thinking, yeah, obviously your result says that the resolved SST features have an influence, but I was thinking about all the other high resolution processes that get, that work between the surface and the upper atmosphere. How many more of those were resolved? Sorry, that wasn't a question. I was just saying the result is very interesting.
Yes. Thank you.
I will say the atmosphere resolution changed as well as the ocean resolution.
I have a question for Thomas. So thank you for a nice talk. So actually, I'm really curious about the relationship between the oceanic frontal impacts on the single cyclone and the as a recurrent storm track activity as a recurrent of cyclones. So yeah, in your talk, the argument that the absolute SST matters for a single cyclone, I think it assumes that assume a infinite interval of the cyclones. I mean assuming that the cyclone preceding cyclone does not affect the trailing cyclone. But I think, of course, the reality, the real situation, this is not such kind of a idealized situation. And I think in your talk, I mean, especially in the latter half of your talk, the climatological mean impact, or kind of, for example, the sloping, the analysis of the sloping is related to the kind of recurrence of the storm track activity. So I think the combining or incorporating the perspective of single cyclone and the storm track activity as a recurrence and a group of cyclones would be really informative, especially for the connecting the understanding of the synoptic scale and the basin scale atmospheric response to the oceanic fronts, I think. So I'm wondering whether you have such kind of a plan to tackle this kind of thing.
Yeah, thank you for your question. So, of course, so in this idealized world, you just see the one cyclone and there's not really a preceding cyclone. But there's still a lot of latent heat fluxes ahead, right? So that's what fuels the cyclone in addition, right? So because the relative humidity we prescribe is the same everywhere, right? So there is an effect from the SST even in this single cyclone simulation. But of course, I fully agree with you that then in the storm track, it's a chain of cyclones, a family, right? And then they all pass on stuff. So we're actually looking into that, yes. The thing though then seems, so what we propose now as a hypothesis, it comes down to moisture availability and how the ocean makes it available and how that goes together with the atmosphere and harvesting it, right? So I don't have an answer how that works, but that's what we're investigating at the moment, both from what I showed like a phase perspective, so you integrate up the storm track, but we're also trying to go into the evolution of, we call them families of cyclones. So in other words, so there's a cyclone, and actually the preceding cyclone leaves more moisture and baroclinicity behind for the next one, which is very counterintuitive for baroclinic instability, because you would say a cyclone's job is to reduce baroclinicity. But actually we find incidents where a cyclone increases baroclinicity through latent heat release, which has to do with provisions from the ocean. Yeah. So that's something we're looking into.
Thank you very much.
You there?
Yes, hi. It's a more general question to all of you. So most of the studies focus on mesoscale SST, for example. And what about sub-mesoscale in the ocean? I mean, we can have a much sharper fronts, larger heat fluxes. So do you have any idea or what would be the effect of those sub-mesoscale features? And do you have any plan to assess it?
So I had a long-standing interest in this, and to me, seems I would toss the question back, and I would basically say I think we have already seen evidence for that. Is if you increase the structure in the ocean with these eddies, it seems like you increase the net output in terms of what I now argue for, mainly latent heat, for example, right? So if there's a coherence between this, then I think we can start connecting some dots. Yeah.
Justin, do you have any response to that?
Oh, just probably these atmospheric systems spend less time over the sub-mesoscale, so that's another thing to wonder about how they feel the sub-mesoscale. And there's just been a few papers, but not that many. I think there may be some people in the audience, but it's not as big a field as the mesoscale.
Yes, it's shorter but then stronger. So I have no clue, but.
I can just comment on this. So I would also, I mean, the paper I didn't comment on, but we looked at how fronts interact with fronts, like atmospheric fronts with SST fronts, so not mesoscale eddies, but as just so the atmosphere is very fast, and these ocean eddies sit there. So And I think this reloading of moisture that I commented on is mainly when there's maybe not so much action in the atmosphere. So there might be a big cold air outbreak or other situations where there's just this climatological pumping up of the, whatever heat and latent heat there should be.
I think I agree.
Oh, yeah, go ahead.
I think I agree with Justin and Tom's. So we should think about the different response of the atmosphere and the ocean, since the ocean signals will be persistent for a long time scale, right? Yeah. Thank you.
Right, Tom, yeah.
Thank you. I have a question that's probably more specifically to Xiaoqi. Does the CSM high-resolution couple model consider both the thermal and dynamic coupling, the latter being the wind and current coupling?
I think I'm not quite understanding your question. So it's about the CSM coupled.
Yeah.
Yeah, I think so. So it's a fully coupled climate models. So
Okay.
also including the atmosphere and the ocean and also CIS part. So it's which fully coupled. Yeah.
That's great. So then my real question is the impact of the small scale SST on the, the omega and the secondary circulation. Are you planning to look at the relative contribution of the SST effect and wind current coupling effect on their vertical motion?
Yes. So because since until now I only focused on the omega anomaly after the high pass filter, right? So we will think that it may have an impact not only the local influence but also the remote influence. So and after that, I think I will also check the relative humidity, which is responsive to the diabatic heating and also consistent with the moisture transport. Yeah.
Okay. Thank you.
And Xiaoqi, to follow on, when the filter, I think, just applies to the SST, is that?
No, it's also for the omega. So
For the, what I mean is it does not affect the relative wind effect. I think the currents are not.
Oh, yes. Yeah, the current is not.
Right. But the modeling infrastructure that you have allows you to look at the wind current coupling, high pass filter effect as well, right?
Yeah.
Thank you.
Thank you.
Eric?
So I just wanted to pose a discussion question to our speakers and to anyone else in the audience who cares to chime in. There's a big, what you presented is a good case that the ocean is important for the predictability of precipitation or storm track variability. And I was just wondering if you could comment on what we need observationally to improve subseasonal to seasonal prediction of the storm track and precipitation, or what we would need with models. Do we need coupled models? Do we need higher resolution? Are there more diagnostics that we need to do? And I was just, it's a little bit of a broader question, but I think that's one of the key outcomes of this workshop, if we can get to that.
Yeah, observations. So then we would first need to know what the models really struggle with to some extent, I would say. So, I mean, like, we all know that we still struggle with surface fluxes, especially when it's high winds, right? So maybe there's something that could be done there. But I'm also wondering, so one thing is that's more like processes then, right? So how can we improve the processes? But I think it also depends what kind of modeling we're talking about. So if it's just short-term weather forecasting, then it's a lot about also getting the moisture content right now at the initialization time as correct as possible. It seems like that matters a lot. And then also not only maybe in situ observation, but also satellites come in probably very prominently, I would assume. But I'm not so into observations, I have to admit. I mean, I just know I do a lot of more higher latitude coupled work, and then of course the coupling to the ocean is very important because as was addressed earlier, the mixed layer might be very thin, but then you might punch into a warm current below or so, and that even can happen on like 2 or 3 day forecasting timescales. So then the coupling is very essential. In the western boundary currents, that might not be as essential. Yeah. I'm not sure.
It's like in terms of like observing system, for example, to improve the weather forecast of like atmospheric front, like Thomas, you're showing this assist the front peak of the moisture and downstream proportion of the front has a huge implication about how we design the sampling strategy or right spacing or stuff like that. Do we need to measure directly on the the atmospheric front, or do we need to think about broader spatial scale observing system, right? So I think that kind of discussion will be very important, and modeling study can inform planning for the observations.
Yes. I think that's very interesting what you say with the scales, right?
Yes.
So I think it's still very interesting to understand the hydrological cycle across the SST front. I think that would be really interesting if one can get at that somehow, right? But then it's the same what you say. That's a bit more like, as I showed, the cyclones seem to care most about the moisture that they suck up, which is a much more larger scale endeavor what they do out there, right? So, but as I showed, like I think the hydrological cycle across the SST front is something that determines a lot, also in terms of restoration of the moisture, I think. So that is a bit more localized, maybe.
Yes.
We have a question online. Sam, if you want to unmute yourself.
Yeah, Samantha Wills here. I was just commenting on what we can do potentially to improve the observations along the lines of those air sea heat fluxes and what Yolande said earlier. We actually put in a proposal with the Weather Program Office to leverage the existing coastal weather buoys that are along the East Coast and near the Gulf Stream, and trying to get those subsurface measurements in so that you can look at the ocean heat content in the column there, and also trying to get an actual more direct estimated bulk flux measurements based on having those co-located atmospheric and oceanic variables that you would need. So, I think thinking of ways that we can leverage some of the existing infrastructure would certainly help us, at least in the short term. Before, of course, there's lots of thoughts in terms of how can you expand the entire observing network. But I definitely think getting a lot more of that ocean resolved in observations is very important.
Thank you. Benjamin? Yeah.
Yes, Benjamin Jaimes de la Cruz from the University of Miami. I would like to add a comment and at the end a question to Thomas. So basically, regarding the last question, what we need, based on my experience working in hurricanes in the Gulf of Mexico and the Caribbean, basically what we are trying to do to understand this Earth's interaction over the mesoscale ocean field is to have collocated measurements of atmospheric properties and the ocean, not only the SSTs. Especially during summer, the SSTs can be homogeneous in the Caribbean and the tropics. And what actually it's making the difference is the interior structure of the ocean, at least the upper 100 meters, or in some cases, the upper 200 meters of the SSTs. NOAA has deployed thousands of atmospheric profilers in these storms. However, in few cases, there are collocated ocean observations, so that makes it impossible to actually have actual estimates for the fluxes, not even measurements of turbulent fluxes, but estimates based on the bulk formula, right? So that's a big open issue that needs to be addressed to understand these interactions, at least for the extreme cases. And now going back to my question is that in the tropical cyclone community, the intensification of this storm is seen as a competition between fuel and anti-fuel, being the fuel, the air sea fluxes, and the anti-fuel, the dry downdrafts that result from convection in the storm. So basically, in the tropical cyclones, you have an inflow that can be contaminated with the anti-flow, with the dry air, and how this is replenished by the air sea flux is actually going to have an impact in the tropical cyclone intensity. So I was wondering if that replenish that you are seeing in your experiment is part of the inflow layer in that cyclone, that it's actually compensating that effect that we notice in the tropical cyclones.
That's a very good question. So in the idealized simulations, there's not necessarily a drying or these downdrafts downstream, right? So it's basically you set in one cyclone to develop, and it's very pristine ahead, sort of, right? So there's some downstream development. It's not as significant as what you were saying, that there might be something that dries out the air before and then it's replenished. But I think there could be, I said, you can prescribe something in your model to do something like this. So I think it also gets at what I was saying earlier. I think what's really interesting, what is the time scale of replenishing water in the atmosphere through the ocean? I think that's kind of the key. I'll have a comment for the other part, though, and this is more to the oceanographers. So I totally agree that it's undersampled what's below the sea surface, right? And we did a lot of work, like cold outbreaks in the Nordic seas, right? And the problem when you co-locate observations in a highly dynamic ocean, so this is at the western, this is the boundary current, right? So the West Spitsbergen current, and then it comes back at the East Green current. Mm-hmm. The problem then is this competition, right? So you have the sea forcing, sea surface forcing, and then you're trying to see something co-located in the ocean, but the advection is so strong. And actually the advection of the heat in these boundary currents is so strong that it's very difficult to actually identify the signal from the surface. So if there's some smart oceanographers around, that's something we should discuss, I think, how to really disentangle this. And I don't see how you can do it without incorporating ocean models into the analysis.
Yeah, I think that's one of the breakout questions is this how the models can inform the observation strategy and vice versa as well. So I guess I think it would be good to get the feedback from the audience about that aspect. Do you have any more questions from the group? And nothing from virtual participants? Okay, then thank you very much again. And we have a lightning poster talks from the that I think Sam, you can lead it or okay.
Yeah, I'll take over from here. Thanks, Yode. Yeah, so for those of you who might have missed a portion of one of my lengthy emails, in an effort to make it a more equitable experience for those who are virtual and submitted poster abstracts, we will do brief lightning talks for each of those poster presenters. So we'll have one of these sessions today and another one tomorrow. So if we could pull up those slides, thank you. And then I think first up is Agostino.
Good morning, everyone. My name is Agostino Meroni. I work at the University of Milano Bicocca in Italy. And well, I will not be talking about the metrics on pressure adjustment that was mentioned earlier, but I will be happy to chat about it if anyone is interested. Today, I will be presenting some work we are doing on the fast atmospheric response in terms of surface wind. So the fast response to SST forcing. And so I'll focus on the instantaneous wind response and the role of environmental conditions. From this first slide, I want you to focus your attention on the panel in the middle, where we're comparing the beam distribution of surface wind divergence as a function of the downwind SST gradient for different data sets. So the green line is showing monthly data set, and we see a linear relationship. So the slope of this linear relationship is the coupling coefficient. And if we take satellite data at daily resolution, we get the dark blue line. So we extend the range of the forcing field and the response field. And we also notice some nonlinearity in this relationship. But we also considered simultaneous and collocated data, because on the METOP-A satellite, we have an instrument for SST and an instrument for wind field. And we see that with this collocated and simultaneous data, we get stronger coupling. Next slide, please. All right. We also did a step further. So we tried to separate this coupling for different seasons. And we noticed that in winter, in the northern hemisphere, we get the weakest coupling. And to interpret this, we did some analysis on two environmental conditions, mainly the background wind speed and the air sea temperature difference, using daily reanalysis dataset. And we can chat about this later during the poster session, but we found that the air sea temperature difference is the controlling parameter for the seasonal modulation of this coupling. Thank you.
Check. Oh, all right. Thank you, Agustina. And who do we have up next? Oh, Young-hee Yoon, if you'd like to take it away.
Hello, my name is Young-hee Yoon. I'm a graduate student at Busan University in South Korea. I'd like to talk to you today about my ongoing research. Global warming effects on oceanic mesoscale eddy energetics. Mesoscale eddies are ubiquitous features of the global ocean. They have a critical role in the mixing and transporting of heat through biogeochemical properties across the global ocean, and thus can regulate the regional and global climate. A recent study revealed that the regions already rich in eddies are getting even richer during decades. However, it remains unclear how greenhouse warming effects reorder eddy activity through the lack of the observation, long-term records, and high-resolution simulations. So we try to understand the responses of the eddy activity to greenhouse warming effect using ultra-high-resolution simulations. First figure shows that the spatial distribution of the global eddy kinetic energy. Our model simulation reveals that greenhouse warming leads to non-uniform and heterogeneous changes across the globe. If eddy kinetic energy averages on this area we are looking at, eddy kinetic energy has increased in all the regions except for curve stream. Next page. How can I? Oh, thank you. To zero in on the western boundary currents in northern hemisphere, we can compare between two regions. The first closure current, second Gulf Stream. For closure current compared to the present day, the kinetic energy increased 4% in doubling CO2 warming and 4.1% in quadrupling CO2 warming. Under greenhouse warming, closure currents are getting stronger. Stronger closure current enhance the mean current gradients, resulting in paratropic instability. For curve stream, the kinetic energy decreases 7.1% and in doubling CO2 warming and 26.9% in quadrupling CO2 warming. The curve stream, as part of the Atlantic meridional overturning circulation, slows down as the surface salinity in the high latitude decreases under global warming. Related to this mean state change, all convergence processes contribute to suppressing the kinetic energy, especially in the reduction in the buoyancy flux work has dominant. On the other hand, how did the effect of current feedback change under global warming? Regarding the mesoscale dynamic coupling, we are studying eddy wind work. Regions with the positive eddy change we saw the previous sheets shows the enhanced eddy killing effects. Thank you for the listening.
Thank you. And we'll go on to our next talk, which I believe is Marta. I saw you there a minute ago. Marta,
Yeah, okay. Hi. Can you hear me? Okay. Okay, so I'm going to present briefly the Gulf impact
project and our case study that we carried out last year. In the Gulf Impact project, we are focusing how air sea interactions over the Gulf Stream, colder outbreaks, resulting surface fluxes, and how they affect the formation of cyclones, the warm conveyor belt of the cyclones, and downstream the formation of atmospheric blocking. And first, we focus on an atmospheric block that was over Europe, over Western Europe in February 2019. And this block, it's a quasi-stationary anticyclonic system that stayed there for a week and caused a heat wave, which resulted in that in February we had temperatures above 20 degrees. And we studied this using Lagrangian trajectories. You can see down there that there is this small image how trajectories look. And we ran them from the Gulf Stream forward and also from the block backward. And what we wanted to see is like how many trajectories interact with the Gulf Stream. So we first look at the backward perspective, and we found that around 1/5 of those that start from the block actually passes over the Gulf Stream in the atmospheric boundary layer. But when you look from the forward perspective, it was this number was changing with the cyclones, because this case study was also associated with the clustering of cyclones over the Gulf Stream. So when we had the rapidly intensifying cyclone, this number was much higher of trajectories that actually ended up in the block but started from the Gulf Stream, and increased even to 90%. What is interesting is that all of our trajectories were diabatically heated. A lot of them were identified as colder outbreak ones, and also warm conveyor belt ones. So we had this rapid ascent into the upper troposphere. Next slide. And what's important is then we divided the trajectories into those that started from the block and we ran them backward 10 days, and those that interacted with the Gulf Stream and those that didn't. And those that interacted with the Gulf Stream actually picked up moisture over the Gulf Stream region in the Western North Atlantic. But those that didn't, they mostly pick up moisture in the subtropical ocean and also ascended them into the upper troposphere. And then in the upper troposphere, they were advected into the block, so that they didn't interact with the cyclones that occurred in the Western North Atlantic. And what's important is that those cyclones, we had the presence of the handover mechanism. So one cyclone, as I said, we had a clustering of cyclones, was creating conditions for colder outbreaks. So we had this large surface heat fluxes over the southern side of the Gulf Stream. And then another cyclone was traveling into this region, picking up this moisture, and the air parcels that were already moistened and heated by another by this colder outbreak were then lifted into the upper troposphere. And this happened from one cyclone to another. So this is this preconditioning mechanism and handover mechanism already mentioned in several studies. And in the end, I just want to mention that also a poster that will be presented in the poster session about the Nordic campaign. And in this campaign, it's planned for by KIT mostly, but also many other institutions around the world for 2026, which will be focusing on measurements over the Gulf Stream with a focus of atmospheric rivers, the downstream effects, and especially the downstream effects over Western Europe, dry intrusion, and extreme weather. Thank you for your attention.
Thank you, Marta. Next up, we have Pablo Fernandez.
Yes, good morning. So my name is Pablo Fernandez, and I'm a PhD student in Paris in Laboratoire de Météorologie Dynamique. And in this brief presentation, I will be briefly showing my research. So my research is focused on how ocean small-scale surface features in different, which we can identify in different variables, affect latent heat flux, typically in the Northwest Tropical Atlantic Ocean, so the region on the map in the figure, where a large campaign called the Eureka campaign took place during the winter of 2020, and lots of in situ data from the ocean and also the atmosphere and air sea interface were collected. And in a second step, I'm also interested in which mechanisms are operating between the ocean and the marine atmospheric boundary layer, and which mechanisms drive latent heat flux. So I am using a bunch of different data sources. So we have satellite observations from different kinds, reanalysis, and also some of the Eureka in situ observations taken during the campaign. Next slide, please. Yes, so in the first step, we are interested in assessing how the SST small scale features affect the fluxes. And so for that, we propose a linear algorithm to downscale the latent heat flux based on exclusively on SST. And what we find is that we have indeed a large increase of latent heat flux of the order of 30 to 40 watts percent with respect to the climatology when we increase SST per 1 degree. And that this change is really different depending on the sub-region of the Eureka region of the Northwest Tropical Atlantic Ocean we are in. And we divide this increase and this variation in two different mechanisms. So the first one is the dynamic mechanism as a consequence of the thickening or solar wind of the marine atmospheric boundary layer as a consequence of the SST anomalies. And this mechanism is also present when we include the small scale observation onto the latent heat flux and accounts for 28% more or less of the change. Secondly, we have a thermodynamic mechanism, which is just the result of the fact that warmer air is able to hold more moisture, and it only accounts for 5%. So the conclusion here is that by including the small scale SST features, we can really obtain better estimates of the latent heat flux, and in fact, the mechanisms driven by these small scale SST features are the dominant ones in the latent heat flux variation. And in a second step, we are using cellular data, so in situ data from the Eureka campaign, to see how the SSS, so the SST variations via the SSS anomalies affect the fluxes. And so we separate, we identify different water masses, which are represented in the different panels of the second figure. And we try to see how the mixed layer depth certification affects the fluxes. And indeed, we would expect that lower sea surface salinities would be associated with reduced water entrainment from the deep ocean and increased heating rate of the mixed layer depth, and that, in fact, would lead to an increase of the flux. However, when we look at the freshwater plume associated clusters, we see the contrary. And so we are now trying to elucidate the different mechanisms operating and which may explain this contradiction. Thank you very much.
Thank you, Pablo. Next up is Sunil.
So I'm Sunil Iyer. I am currently a postdoc at Oregon State, but this work was done as part of my PhD at the University of Washington in collaboration with Kyla Grushka, Jim Thompson, and Elizabeth Thompson. So our primary goal is to look at how small-scale spatial variations and surface currents and sea surface temperature affected air-sea momentum and heat fluxes, which is, of course, a topic that has already received a lot of research attention. However, our work was focused away from boundary currents and coastal features with strong gradients and the Northwest Tropical Atlantic trade wind region. So we deployed two types of platforms, both of which measured all the standard state variables in the atmosphere and ocean, as well as directional wave spectra from which we can calculate both momentum and heat fluxes. So if we could go to the next slide, please. The left hand, and so these two panels highlight some of our key results. And if we focus on the left-hand side first, what's plotted here is air-sea momentum flux derived from wave spectra and assuming equilibrium wave theory as a function of wind speed, with gray points representing individual observations and the colored lines representing data that have been separated by wave and current alignment and bend by wind speed. And the main point here is that that black line is elevated above the pink line pretty consistently at moderate to high winds, which tells us that when waves and currents are in opposition, that we observe higher momentum fluxes compared to when waves and currents are in the same direction. And doing some further sensitivity tests, that is due to both changes in the current relative wind, or that direct effect of surface currents on the stress, but also wave current interactions, which have not been studied in a lot of detail in the open ocean. If we go on to the right-hand panel, that the plot on the left-hand side of that shows a map of sea surface temperature from a 4-day period, typical of what we observed during this field campaign. So we can see that SST increases pretty significantly going from west to east across this persistent feature on scales of tens of kilometers or so. The scatter plot on the top right shows sensible heat flux as a function of distance across that feature. And we can see that sensible heat fluxes are consistently higher on the east or warm ocean side of this gradient, which implies that SST plays some role in modulating the spatial variations of air-sea heat fluxes on these scales. So as a whole, these results demonstrate that both momentum and heat fluxes can vary quite a lot on scales of tens of kilometers or so, and thus could be a source of uncertainty in any larger scale applications that don't resolve these small scale features. Thank you.
Thank you, Sunil. Okay, next up we have Samantha Hallam.
Oh, hello. Thank you. I'm Samantha Hallam from the Irish Climate Analysis Research Unit at Maynooth University in Ireland, where I'm a postdoc. And this piece of work looked at the land and ocean comparison of the variability of the Northern Hemisphere jet stream between 1871 and 2011 using the 20th century reanalysis dataset. And first of all, we looked at the seasonal variability. And what we found was that the jet stream was tightly confined in the wintertime over the western boundary of both the Atlantic and the Pacific in the region of the Gulf Stream and the Kuroshio Current. And we also found that the seasonal jet latitude range between December and January was also 10 degrees lower over the Atlantic compared to over the Pacific. Which is where we've got the Atlantic meridional overturning circulation, which transports 1.3 petawatts of heat northwards. We also then looked at the decadal trends in terms of the Atlantic and the Pacific, which are shown here. We found two distinct differences over the time period. So we found increases in the jet latitude of 3 degrees northwards, so a poleward migration in jet latitude over the Atlantic, and an increase in the jet speed of around 4.5 meters per second. Whereas over the Pacific, we found lots of interannual variability over the 141 years in terms of both jet latitude and jet speed, but we actually found no decadal trends. And I guess one of the key differences between those two ocean basins is obviously you have the AMOC in the Atlantic. And then the third thing that we looked at was the interannual variability. And in the Pacific, we compared it to the Pacific decadal oscillation. And what we found there was that the PDO explained around 50% of the winter variance in the jet latitude on timescales of around 20 years. And the direction of the arrows in this covariance here indicate that the PDO was anti-correlated and that the PDO was leading. So very happy to chat more with our poster later, and you can download the poster using the QR code that's here. Thank you very much.
Thanks, Samantha. Next up, we have Jiu from Jiu Lee.
Hi everyone, my name is Xiaoqi. I'm PhD student in Department of Climate System, Busan National University, South Korea. The title of my presentation is Global Warming Effect on Ocean Horizontal Stirring Characterized by Finite Size Lyapunov Exponents. Ocean horizontal stirring is two-dimensional turbulent phenomena that promote mixing speed by deforming the fluid into an elongated shape. It is almost everywhere accompanied by other dynamic oceanic processes such as eddies, meandering currents, and fronts. So the question is, how will ocean horizontal stirring respond to global warming, and I use finite Lyapunov method, and this is on Lagrangian metric that characterizes the dispersion rate of two infinitesimally close particles as an exponential function in a chaotic system. So right side figure represent the FS31 one-day snapshot, and this FS30 gives more detailed, more details. So FS30 is more complex and gives a more detailed description of the mesoscale phenomena. Next slide, please. To analyze how FS30 changes with CO2 concentration change, so I use the high resolution experiments based on the fully coupled community Earth system model version 1.2.2. The three so there are three experiments. One is present day control one and double CO2 and quadruple CO2 conditions. So I use the daily UV components at 15-meter depth, and the ocean horizontal resolution is 10 kilometers. So we can see mesoscale phenomena in the ocean. So right side, I've been shown how the FS30 changes globally. The significant changes were in the Arctic Ocean, Southern Ocean, and Western boundary current regions. And so the Arctic Ocean in particular, we can see large changes in response to sea ice loss. And in my poster, I presented possible mechanisms for this. So thank you. This is all of my presentation.
Thank you. And then last but not least, we have Chris Zappa. Are you on here? There you are.
Hello, everyone. This poster, I'm going to talk about using ship-deployed, high-endurance uncrewed aerial vehicles to study ocean and atmosphere boundary layer processes. You can start the movie. So this is a movie of these UAVs that we use from ships. They have complete autonomous takeoff, flight, and landing.
Okay, everybody on the deck ready?
You muted?
Okay, VTOL's armed.
Ready for a spin check?
Okay, here we go. Launching in 3, 2,
Sorry about this, Chris.
Right.
1. Launch now.
Thanks. So we can fly two of these at a dual UAV operations for continuous flight. They have a high endurance of around at least 8 hours. We can fly a number of payloads that measure direct covariance fluxes, long wave and short wave hemispheric radiometers to measure up and downward long wave and short wave radiation, thermal infrared imaging, visible hyperspectral imaging, but they also have a capability to telemeter data beyond 50 nautical miles at 100 plus megabits per second bandwidth. So you can do real-time control tasking of the aircraft. You could also actually use it as a primary UAV for a squadron. You could go out even further distances, maybe more than 50 nautical miles. Go to the next slide. Next slide. Thanks. So it allows you to provide eyes over the horizon. So you can have your mission control back at the ship. You can go out, look for those, in this case, mesoscale fronts. We were looking for cyanobacteria. You can see there in the bottom middle slide. You can bring the ship over to where the front is and then perform our small scale process study. So in the upper right shows the mapping of this front from the UAV. And then so on the left is the visible hyperspectral imaging, on the right is the response to the thermal structure, SST, and then the bond relay response going across some of these fronts. And if you come to my poster, I can go into more detail about how the cyanobacteria fronts impact upper ocean heating and the overall heat budget. Thanks. And then the next one. So I have a second poster. This one's about direct measurements of air sea momentum flux, near surface currents, and wave hydrodynamics using a hybrid imaging system. So this takes advantage of a few imaging techniques. One is thermal infrared imaging of the ocean surface. There's a few techniques to get velocities at the ocean surface. This one I demonstrate here in the lower left is using what we call the effective surface, which invokes Taylor's frozen turbulence hypothesis to back out what the surface velocity is. Then in the middle one, there's a technique that we use where we measure the surface slope directly from polarimetry. And using these polarimetric images, we can compute the directional wave number frequency spectrum and then use the downwind slice to get the Doppler shift between the upwind and downwind portions. And then this allows us to get the mean surface current in the top few centimeters, and then we can back out what the orbital motions are. If you go to the next slide. So if we take advantage of using multiple, there's a third technique where we can actually sample the viscous sublayer. If we use multiple thermal cameras, we can look at multiple depths, and we can get, using that same technique to get the velocity from the infrared imagery, we can get the velocity at various depths, 3 depths in this case, and we can capture the direct viscous tangential stress. So we can look at things like how much of the total stress is partitioned into the viscous and/or form drag. And we can, from the same polarimetric imaging, we can get an idea of what the total momentum flux is, the form drag is due to waves, over the waves. And on the right is just our first laboratory estimates compared against previous laboratory estimates of this new technique to measure the tangential viscous stress. And it falls in the range rather nicely. And if you come to the poster, I can talk more about that. Thank you.
Excellent. Thanks, Chris. And thank you to all our Lightning Talk presenters. To remind everybody in person and online, we are hosting all of those posters on the US CLIVAR website, and you should have a link in the Know Before You Go email that you got on Friday.
All right, so now we're into session 3, feedback of the atmospheric responses onto the ocean. And the first talk is Lionel Renault, who is going to talk about modulation of ocean dynamics by sub-mesoscale ocean wave atmosphere interactions, current knowledge, and limitations. So Lionel, go ahead.
Hi. Oh, okay, it works. Sorry. Okay, so it's very nice to be here in person. So, since the pandemic, it was a bit difficult to do everything on Zoom. So my talk is on the modulation of ocean dynamics by sub-mesoscale and mesoscale ocean wave atmosphere interactions. So I wanted to do a kind of a brief overview of our current knowledge and limitations. So I first wanted to start my talk with those two nice pictures. So the first one is derived from Eddie Rich global couple model from Mercator Océan in France. As you know, the ocean is characterized by large-scale currents, obviously, such as western Atlantic currents, the Gulf Stream here, the Agulhas current here, but also by mesoscale features. For example, those nice wings that shed from the Agulhas currents here and that travel through the Atlantic Ocean. But actually, also, if you look on this second picture, so this is from a sub-mesoscale permitting ocean model. You can see here the central jet of the Gulf Stream with some eddies that detach from it and travel westward, but also a lot of very fine scale structures. So basically the sub-mesoscale features currents in the ocean that create with the mesoscale eddies and structures a non-uniform surface for the atmosphere. So those features are known to have a large influence on the atmosphere through SST gradients, SST anomalies, and surface currents through two main RC interactions. So the first one that has been historically assessed is the thermal feedback, which is essentially the atmosphere response to surface SST anomalies and gradients. So I illustrated here from that nice picture from CO 2017, which represents the correlation between the wind speed anomaly and the SST anomalies, where we can see positive correlations. So basically, it shows that the ocean drives the atmosphere and not the other way around at mesoscale. There is then the current feedback, which is basically the influence of the surface currents on the overlying atmosphere, and that induces, as I will present in this talk too, some mesoscale, some sinks of energy from, for example, here, from mesoscale eddies to the atmosphere. And most in this talk, I'm going to talk mostly about mesoscale thermal feedback and current feedback, but I will also introduce some sub-mesoscale work, and as a perspective, the wave feedback, the surface gravity wave interactions with sub-mesoscale currents. I won't focus on RC land interaction in this talk. So to start, so the thermal feedback. So I wanted to introduce this plot because it has already been introduced in the previous talks this morning. So it's a famous plot from the Shelton with a wind blowing over from cool to warm water. So basically, it has been shown in the past that using satellite data, that SST feedback to the atmosphere has two main pathways that can impact the ocean. So the first one is through the wind anomalies. So we can see it here from satellite data, QuizCat and SST observations, that the SST mesoscale anomalies induces wind anomalies and curl anomalies that can have then an impact on the Ekman pumping in the ocean. We can see it here. But actually, one of the questions was, okay, we have a strong wind response, wind and wind stress response to the SST anomalies, but from an oceanic point of view, do we care? So there is a first study from CO 2016 that suggests that this feedback does not have a large impact on the ocean dynamics, on the mesoscale eddies. It may have an impact on the eddy propagation, but not directly on the mesoscale activity, on the EKE budget. We confirm it recently, actually it's a paper under review. So here we have a simulation with both current and thermal feedback, a mesoscale simulation over a realistic tropical channel, 1/12 of a degree compared to an atmosphere. And here we have one where we remove the current feedback, so we just have the thermal feedback at the mesoscale. And here we have a box plot of the baroclinic conversion of energy, basically W prime B prime. And we can see that basically we just have a random response around 0, and the net response of baroclinic instability, baroclinic conversion of energy to the thermal feedback is basically 0, so we don't have an impact of the wind anomalies induced by the thermal feedback on the eddies, on the generation of eddies. It may have another impact on the wind work, but the wind work basically is the exchange of energy between the ocean and the atmosphere. But if you look in the Coppet simulation here, for example, over the Agulhas currents, where we have the thermal feedback and simulation with a spatial resolution of 6-7 kilometers, basically we just have noise because we have only 5 years of simulation. And it means that we don't have any net exchange of energy between eddy and the atmosphere, so that the wind anomaly do not impact the eddy fields in the ocean. But there is another pathway, so the second pathway via the surface heat fluxes. So basically the sensible and latent heat flux. So this is the correlation between the turbulent heat flux and the SST anomalies from Kirkman et al. 2012. We can see that we have a positive correlation. So it means that a positive SST anomalies will induce a larger heat flux. And from an oceanic point of view, actually, if you look the energy budget of the eddies, so this is a picture from Bishop et al. 2020. We can see that those heat flux anomalies induce a transfer of potential energy from mesoscale eddy to the atmosphere, almost everywhere, and especially over western boundary currents, where the eddy activity is larger. And there is a nice paper of Maeta 2016 that provides this cartoon here. So basically, those things of potential energy will act on the eddy generation at the mesoscale through a pathway from the mesoscale available potential energy to the atmosphere that can reduce basically damp the EKE, the mesoscale activity, by reducing the conversion of energy from baroclinic from potential energy to kinetic energy, basically. But actually, we had a kind of controversy here because in Maeta 2016, they suggest a dumping of about 10 to 20%, but in the paper of CO 2016 for the California West Coast, they did not find any impact. And actually, it may depend on the filter used. Actually, in those kind of simulations, to isolate the SST effect, what we do generally is to smooth the SST sent to the atmosphere. So the SST in the oceanic model remains the same, of course, but the atmosphere will see only a smooth field of the SST, basically without mesoscale eddies. And in CO, they use a 300 kilometer filter and a 100 kilometer filter in Maeta, and may explain the different results they obtained. So we did some tests in our simulation, the same tropical channel simulation over 5 years with different kind of filter, one of 300 kilometers more or less and one of 1,000 kilometers. And we find that we can have a EK damping of about 10% when using a 100 filter size, and a very small, basically a negligible damping of 1% when using only a 300 kilometer filter. So basically, there is a real mechanism here, a transfer of potential energy from the ocean to the atmosphere, but that have a mild impact on the ocean dynamics. At the sub-mesoscale, so it's not really well known. Actually, there is not that much studies, so we are missing some studies to better understand how does it work at sub-mesoscale. So there is a very nice paper of Igor, but he's not here, so I think Jacob will present it for him. They use an oceanic open simulation of the US West Coast with a spatial resolution of 500 meters. So we have some mesoscale features here, for example. And basically, they show that we have more or less the same mechanism that at mesoscale. So here we have the simulation without the mesoscale sound feedback. It means that the atmosphere cannot see the mesoscale SST anomalies. And in blue, we have the control run simulation, so in which the atmosphere can see the SST mesoscale anomalies. And basically, they found that there is a reduction of the potential energy in the ocean because of this flux from the ocean to the atmosphere, inducing a reduction of the EKE. But actually, the reduction of the EKE is partially compensated by a reduction of the eddy windwork. So as I will show you after, the eddy windwork at those scales acts as an eddy killer. So basically, we reduce the sinks of kinetic energy that partly compensates the sink of potential energy. So this should be, we need more observations at those scales, and this should be assessed also in other regions, such for example, the Gulf streams or anywhere. So the other main interactions I wanted to discuss is the current feedback to the atmosphere. So it's basically the influence of the oceanic surface current on the overlying atmosphere. So in a bulk formula, in a coupled model, it's very simple to take into account. You just have to use the relative wind to the oceanic currents. Historically, it has been neglecting during a long time under the assumption that the oceanic currents are much weaker than the wind. But actually, recently, thanks to new observations and also to a high-resolution coupled model, we actually found that it was it really matters for both the mesoscale activity, sub-mesoscale activity, and even large-scale currents. So you can approximate it for, doing that kind of development. And basically, what the current feedback we do, it induces small scales stress anomalies and wind anomalies that will then interact with the ocean. I have a simple cartoon here. So this is a simulation without current feedback. Here we have a blowing wind in this way, but it does not really matter actually, the direction of the wind. And an eddy here. On this side of the eddy, we have a sink of energy. On the other side, we have a positive input of energy from the atmosphere to the ocean. When you integrate over the eddy, basically, you have a net exchange of energy of 0. A net eddy wind work, so the cross product of the stress and the surface current of 0. With the current feedback, so with that interaction, you have a larger sink of energy on one side of the eddy, and actually you have a reduction of the input of energy on the other side of the eddy. Then when you integrate over the eddy, you do have a negative transfer of energy from the ocean to the atmosphere. So basically the ocean, the eddies are forcing the atmosphere. And we can see that sinks of energy actually everywhere at many scales, both from a tidal scale, for example, so it's a tidal currents that will induce a tidal winds. We can see here in blue the transfer of energy from the tidal currents to the atmosphere. Then internal tide scales too. At some mesoscale over the US West Coast here, where we can see also those sinks of energy that act as an eddy killer. And at the mesoscale here, from the observations, we can see it from models too. But then with the observation, we have to be very careful because we don't have exactly the same spatial resolution between AVSO. For example, here I use AVSO and QuizCat. There is discrepancy in terms of temporal and spatial resolutions, but we can still see those sinks of energy. And actually, they really matter from an oceanic point of view because they do induce a damping of the mesoscale activity. I compare here for the US West Coast, the simulation without the current feedback, without those sinks of energy, and with the sinks of energy, and we can see that we have a large reduction of the mesoscale activity by up to 44% in these regions. We can find similar results over other regions, and even at the global scale. So here, using a 1/12 degree global Köppen model over 24 years, we can see that we have a reduction of the decay everywhere, and by 30% on average. It's also present at some mesoscale, but we don't really, well, as far as I know, there is only one study in 2018. And actually, it's kind of interesting because at the mesoscale, we only have that sink of energy, the eddy killing, so the reduction of the mesoscale activity by the transfer of energy from the ocean to the atmosphere. But at the mesoscale, we also have an increased Bergen conversion of energy that is induced by the Ekman pumping caused by, related to the current feedback too. So basically, you have an eddy killing effect that is partly balanced by more generation of Bergen stability of some mesoscale currents. But at the end, we still have a reduction of 15%, which is weaker than the mesoscale reduction. And an interesting impact is that, okay, that was basically the local impact. So we do have a reduction of the mesoscale activity, but actually we also have an upscale impact, an impact on the large scale, and for example, on the western boundary currents. So I show it here for the Gulf Stream and the Agulhas currents. So this is actually the flux of energy between scales. So negative flux here means that we have a transfer of energy from small scales to large scales. And a positive flux here means that we have a positive transfer of energy from large scale, for example, 100 kilometers, to smaller scales. And it really matters because then with, for example, the inverse cascade here, it will have a large influence on the Gulf Stream and Agulhas current variability and stability. It's basically the eddy mean flow interaction. And we show that the reduction of the decay also induces a reduction of the inverse cascade of energy over both the Gulf Stream and the Agulhas currents. And it reduces large biases we had in the simulations, in both forced and coupled simulations. So for example, here over the Gulf Stream, In black, we have the path from the observations, and in yellow, we have the path from a simulation without the current feedback, without the sinks of energy. And here we have the same, but with a simulation with the sinks of energy, with the current feedback. And here we have the PDF, the probability density function of the separation of the position of the currents here. So as we can see, the observation is very stable. Basically, the Gulf Stream is always separated more or less in the same position. But in a simulation without current feedback, we have a too large eddy field. Then we have a too large eddy mean-free interaction that destabilize the Gulf Stream and create a too meandering Gulf Stream and a poor path representation in the simulation compared to the observations. When we take into account the sinks of energy, the eddy kinning, we can see that we have a much better simulation of the path of the Gulf Stream and a much better PDF. And it also then have a much larger scale. Okay, yeah, I'm almost done. At the larger scale, then those change actually of the western boundary current path and stability also have indirect effect on the sea surface temperature. For example, here, this is the difference between a simulation with current feedback and without current feedback. So basically, you change the path of the Gulf Stream, then you change the advection of water masses, and then you can have those large dipole of difference of sea surface temperature. I won't discuss here the impact on the atmosphere because it's not the focus of this talk. And just a quick word, so as a perspective, the role of surface gravity waves, because basically they could have a large impact on both the exchange of energy between the ocean and the atmosphere, but also a direct impact from the waves to the currents. And for example, here, a very recent study of Hippolyte 2022, here we have a simulation, 30 meters, so a very high resolution oceanic simulation with ROMs. And here a simulation that is forced with a field from wave watch 3. So there is no two-way interactions here. It's only a forced simulation, but we can see here the vorticity. And we have a drastic change. Basically, there is a large impact of the waves on the sub-mesoscale field, on the frontal-scale and that's it. So we may have also an impact at the mesoscale through other processes, and on the, for example, through the roughness. And so just to conclude, what are we missing? What do we need? Basically, in terms of observations, we really need to have surface currents, temperature, surface temperature, and wind at the same time to have a correct estimate of, for example, the sinks of energy from the ocean to the atmosphere, high resolution if possible, of course, total currents and geostrophic currents. Also, it does matter for the heat fluxes because you should take into account the currents when you estimate the turbulent heat fluxes, especially over the equatorial region, actually. It could be very helpful also to disentangle the thermal feedback from the current feedback effect on the wind, and to better characterize EKE damping and to compare correctly the EKE to the sinks of energy to the atmosphere, to, for example, dissipation by the forecast cascade in the ocean. In terms of modeling, we may need to revisit the bug formula because we may question its validity at a high frequency and with the presence of surface gravity waves. There is some inconsistency in coupled model, for example, between the wave model and atmospheric model in terms of bug formula. And we need more studies on the sub-mesoscale and climate. Just a very last one to conclude. So just an illustration of the behavior of the current satellite observation we have now. So this is a coupling coefficient. You can estimate, I will just focus on that one because of the time. So this is the coupling coefficient between the surface currents and the wind at 10 meters. You can estimate from the observations, Chris-Cat and Ebisoff, basically. So this is what we have from a model. So here this will be our through. And this is what we have in the observations. We can see that we have a reverse sign, so it doesn't make really sense. But actually, we can reproduce this inconsistency with the model by mimicking the observations, basically. And we found that basically here it's simply because we don't have the absolute wind. We have only the relative wind to the oceanic currents. And therefore, we cannot have a correct estimate of the wind response. It's very important because it drives wind work to force an ocean model, and I think I'm already late. So thank you.
Remind the speakers the folks online can't see your pointer. So if you can say what you're pointing at as well as pointing at it, that would be helpful for them.
Let me just figure out how this works.
Yeah, you can figure that out. So the next speaker is Yubai, who is going to talk about sub-mesoscale wind front interactions, the combined impact of thermal and current feedbacks.
Thanks for the introduction. Hi, everyone. My name is Yubai, or you can call me Luna. I'm a grad student from Caltech. Today, I'm going to talk about some mesoscale wind front interactions, or the combined impact of thermal and current feedback. So why should we care about wind front interactions in the first place? Well, here is a study by Charlton and Xie 2010. The color map here, is showing the wind stress curl, and the contours overlaid are the crosswind SST gradient. And just by looking at it, you can probably see that there is some spatial correlation here. And indeed, if they did this 1D bin statistic on the right over here, that has crosswind SST gradient bins on the x-axis and the corresponding mean values of wind stress curl on the y-axis, there indeed exists a highly positive correlation between these two. And so this suggests that ocean surface properties, in this case, the crosswind SST gradient, has an important impact on the atmospheric wind field. And because this study looks at only SST gradients impact on the wind stress curl, so we call it a 1D thermal feedback. And then you're probably wondering, are there other surface ocean properties that's also modifying the wind stress curl? And indeed there is, and this is the surface ocean vorticity. And here is a map in the California current. This is a study by Renault 2016, and I didn't find a corresponding figure for the wind stress curl, but if there were one, you should probably see that these two are also spatially correlated in a negative sense, and this can be captured by the negative slope here in this 1D current feedback that has ocean vorticity at the x-axis and wind stress curl at the y-axis. And so we see that both the current and the thermal feedbacks are modifying the wind stress curl at the same time. But in a later study by Renault and co-authors, they actually find that current feedback is not contaminated by the thermal feedback. So in this case, when they try to assign the variabilities in the wind stress curl to ocean vorticity, there's no issues. It's totally fine. However, we should be really careful for the case of thermal feedback because it is contaminated by the current feedback. And so in a case when we just grab wind stress curl from the simulations or from a coupled simulation or from our observations, where the two feedbacks are not very easily separable. And in that case, if we try to assign all of the variabilities in the wind stress curl to only thermal feedback, there's likely going to be some double counting or missing components, depends on how current and thermal feedbacks interact with each other. And that's why it is really important and critical to study wind front interactions while considering the interaction between these two feedbacks. So why should you care about the mesoscale wind front interactions? Well, here is the study by Udi et al. 2022. And again, we have the wind stress curl and the sea surface temperature from the Gulf Stream region. And this positive correlation between crosswind SST gradient and wind stress curl can be captured by this positive slope in this 1D thermal feedback. And in this study, they are using a high resolution coupled simulation. And so as we can see, when we have this higher spatial resolution, and we can suddenly resolve those so much stronger SST gradients at the surface, and that leads to so much stronger wind stress curl. And so we can suddenly see this whole expansion of the parameter space we can explore in smaller spatial scales compared with the sub-mesoscale study, which is marked by the black box in this panel here. And so really, standing on the shoulder of these foundational studies, we are really motivated to look at the sub-mesoscale wind front interactions, and especially this joint and nonlinear interactions between thermal and current feedback and how they jointly impact the wind stress curl. And right now we are focusing on the Southern Ocean region. So this is the Drake Passage. And we selected two subdomains with different background energy levels just to compare how the intensity of wind front interactions change. But in this talk, the results are all coming from the energetic region. So let's, okay. And this is the model we're using. It is the coupled simulation that's developed by Dimitri's team up in the JPL, and they coupled the ocean part and atmospheric part together. In the ocean part, around the Drake Passage, we have about 2-kilometer grid spacing there, and so we're basically resolving spatial scales of about 10 kilometer. So, you know, it's like not completely some mesoscale, but it's still smaller than mesoscale, and you know, smaller than mesoscale. So we would expect to see again the expansion of the parameter space there. And so now let's officially look at some results here. And on the left is something we called a 2D feedback. It is a 2D conditional mean plot, and it looks pretty weird at the first time. So I'm gonna walk you through this really slowly. We call this a 2D feedback just because we're now taking into account of thermal and current feedback and their impact on wind stress curl at the same time. So on the x-axis, we have the crosswind SST gradient bins, and on the y-axis, we have the ocean surface vorticity bins. And the color map showing here is the mean value of wind stress curl occurring at some combination of vorticity and SST gradient. And so how should we understand the distribution of wind stress curl here on this 2D plot? Let's look at some schematics first. So in the case where there's only current feedback, or i.e. we keep vorticity on the y-axis, but now we plot something completely irrelevant to wind stress curl on the x-axis, then we would expect the distribution of wind stress curl to look something like this. So we would have negative wind stress curl with positive vorticity because they are negatively correlated. And then we would see zero wind stress curl centered at zero vorticity. And similarly for the thermal feedback, we keep crosswind SST gradient on the x-axis, but if we plot something completely irrelevant to wind stress curl on the y-axis, then we would see positive wind stress curl at positive SST gradient because they are positively correlated. And then we see zero wind stress curl centered at zero SST gradient. And now if we allow these two feedbacks to interact with each other together, and we would expect to see something here, and that's exactly what's happening in this 2D feedback plot. And so in this first and third quadrants here, where the impact of current and thermal feedback on wind stress curl are counteracting with each other, they are canceling out each other's feedback. And when this cancellation is complete, you see this tilted zero line here, and that's this line over here. But in the second and fourth quadrants, where the two feedbacks impact on wind stress curl are really reinforcing each other, these are the regimes where we expect to see the large anomalous values of wind stress curl, especially in this region. And so just by having this sloped zero line here, we can see that current and thermal feedbacks are really interacting with each other at the same time, trying to modify the wind stress curl. And if we push this to a smaller spatial scale than mesoscale studies, we can see that these wind stress curl anomalies are about 20 times stronger. And again, the mesoscale, the parameter range explored in the mesoscale studies are marked by this black box here. And these large anomalous values of wind stress curl can have this great potential to then modify the ocean surface vertical velocity through the Ekman dynamics. And here's just another set of the 2D feedback plot, and this time it's on the wind stress divergence. I'm not going to spend a lot of time on here because you can see the story is pretty similar. We see this tilted zero line here again. So this means that both current and thermal feedbacks are impacting the wind stress divergence. But in this case, I just want to point out that because we're resolving smaller spatial scales, and this is time, the ocean surface divergence is actually assuming the same order of magnitude as the ocean vorticity. And so now we can see this negative correlation between the ocean surface divergence and the wind stress divergence that's being neglected by previous mesoscale studies. Cool. So now we've talked about these 1D and 2D perspectives of trying to quantify this current and thermal feedbacks. And now we just want to do a simple wind stress curl reconstruction based on these different perspectives, just to try to see how much variation in the real wind stress curl can be explained by them. And so we just assume that wind stress curl is some combination of vorticity and crosswind SST gradient with alpha and beta as their coefficients respectively. And there are 4 ways of doing these reconstruction. So the 2D one is from this 2D perspective where we take into account of their nonlinear interactions. And so we solve alpha and beta together and we plug that in. For the 1D current feedback here, we assume that beta coefficient is 0, and we solve alpha as the slope of this line. And similarly for the thermal feedback. And then lastly, we just simply sum the two 1D feedbacks or the reconstructions together as a linear sum, just to compare with the nonlinear sum here. So on the top panel is the simulated wind stress curl. It is taken as the truth. And at the bottom, we have all these four reconstructions. We can see that the 2D and nonlinear sum and the 1D linear sum are both doing a pretty good job at capturing the structure and magnitude of the real wind stress curl. But for the two 1D reconstructions, current feedback is so much smaller than the thermal feedback. And so let's try to quantify these. On the left, we have the percentage of true wind stress curl explained by all four different reconstruction methods. And not surprisingly, current feedback is doing a pretty poor job. Thermal feedback is actually doing pretty well by itself in this time snapshot here, but it's still worse than either the linear sum or the nonlinear sum. And even though the two sums are very close, but you can see the nonlinear sum is still doing a better job than the linear sum. And then we also calculated the domain averaged root mean square error with respect to the true wind stress curl for all four reconstructions. But really, we just want to compare how the 1D ones are doing with respect to the 2D reconstruction. So we are taking the ratio of them. And so the current feedback has about twice as much error, and thermal feedback alone has about 20% more error, and the linear sum has about 5% more error compared with the 2D nonlinear sum. And so I guess the take-home message from this plot is, if we want to take into account of the variabilities or anomalous values in the wind stress curl, we should at least consider both of the feedbacks at the same time, regardless of a linear sum or nonlinear sum. But because we're only resolving scales at 10 kilometers here, and so linear sum and nonlinear sum are pretty close, but I suspect if we push the resolution even to higher, I would expect the 1D linear sum to do a worse job. And as I said, in this snapshot here, the current feedback is so much smaller than the thermal feedback, but their relative importance in controlling the wind stress curl does change with time, and we try to figure out why. So here are some time series for different parameters here. On the top, we have wind speed at 10 meters. On the bottom, we have alpha, or the vorticity coefficient we solved from the 2D analysis. And you see three different colors, and there just means how many days of data we're using to compute these parameters, just to throw in some timescale analysis. And then we can see that across all timescales, the alpha coefficient is negatively correlated with the wind speed. And this is not a surprise because this has been identified by previous studies before. But it does become complicated when we look at the beta coefficient or the crosswind SST gradient coefficient. And first, we scatter it with the wind speed at 10 meters, and we see that they are also positively correlated, but this correlation increases as the timescale. And again, we scatter this beta coefficient with the air sea temperature difference, and we see that as the timescale increases, this correlation drastically decreases. And so we speculate that maybe the high frequency variations in the thermal feedback is controlled by the air sea temperature difference, but because thermal feedback is involved with atmospheric boundary layer adjustments and some downward momentum transfer, and so this might explain why we have this slower response between the thermal feedback and the wind speed. But after chatting with Dr. Schneider during lunch, this could also be because of like the noise and signal ratio. But this is the point of the workshop, so I really welcome feedbacks. And you should take a big pinch of salt on this interpretation here, because this is just a bunch of oceanographers trying to figure out what's happening in the atmosphere. But in conclusion, some mesoscale wind front interactions are so much stronger than mesoscale ones. And if we want to explain the variabilities in the real wind stress fields, we should consider both feedbacks together, and they can be explained by physical parameters such as wind speed and air sea temperature difference. Thank you.
And just like in the previous sections, we'll have all the speakers come back to answer some questions at the end, which will be in 15 minutes.
Thank you very much. So this work was mostly funded by the National Academy of Sciences, and I would like to acknowledge that through a Hugos grant for the study of the Gulf of Mexico. It's going to talk about warm core rings and how they decay, and the impact of current feedback on wind stress work, and Ekman buoyancy fluxes on this decay. So on the left-hand side, you can see a picture of the trajectories of particles that were integrated in a geostrophic velocity field inferred from satellite altimetry. These are snapshots from the famous NASA video, Perpetual Ocean. Thought it was much better than anything I could do myself. So on the left-hand side, you have Agulhas rings detaching from the Agulhas retroflexion and drifting through the South Atlantic. On the right-hand side, you see the Gulf of Mexico. You can see the loop currents looping between the Yucatan Channel and the Florida Strait. And then you have a large loop current ring, which is drifting through the Gulf of Mexico. These two classes of eddies have the particularity to be warm core rings and to be very coherent. In the case of Agulhas ring, they can live for up to 3 years. In the Gulf of Mexico, they can live from 9 months to 18 months. These guys are very, very long-lived, coherent eddies. So why are they so important? Actually, Agulhas rings are the only source of southern Indian Ocean water towards the South Atlantic. And they are believed to participate in the meridional transport of heat and salt to the meridional overturning circulation. So they have an impact on large-scale circulation in climate. Loop current rings, on the other hand, they are the only external source of water for the Gulf of Mexico, and they control hurricane intensification because of their huge heat content anomaly. And they are also important for the occurrence and spatial distributions of severe thunderstorms in the eastern US, east of the Rocky Mountains. Now, why is studying their decay so important? Well, let's talk about the Agulhas rings, for instance. They are coherent. That means they mostly conserve their tracers. Imagine an Agulhas ring drifting all the way through the South Atlantic and collapsing against the Brazilian shelf. Its effect on large-scale circulation is going to be very different than if it just releases slowly its tracers through the basin and its energy decays during all its journey to the western boundary. So it's very important to understand that their transport properties are linked to their longevity, and this longevity is linked to their decay rate and the processes that make these eddies decay. So, for instance, in the case of climate models that now are eddy permitting, Agulhas rings or loop current rings, they are explicitly represented in the numerical solutions. And the processes that control their decay is actually not yet resolved. So there could be strong biases in the transport properties of these eddies, and we really need observation-based estimates of the decay of these coherent eddies. So first of all, how does energy decay? So this is the equation for energy density. So on the left-hand side, you have the rate of change of kinetic energy following a material fluid parcel. It can change, kinetic energy can change through buoyancy fluxes, through the work of pressure force, the work of the wind stress, and the wind stress I'm going to be talking here is the relative wind stress that Lionel discussed in depth earlier. You can lose energy through turbulent diffusivity and dissipation. Available potential energy, on the other hand, is only going to be lost through buoyancy fluxes, and actually it's not a loss, it's a conversion from potential to kinetic energy. Now, how does the energy of an eddy decay? Well, if we integrate the energy density equation over the surface of an eddy that is bounded by some boundary C, we integrate it also over the depth of the eddy. There are a few mathematical tricks like the use of Leibniz integration theorem and Reynolds transport theorem. But so we get this equation that says time variations of total mechanical energy, that is kinetic plus potential. Variation is only possible through energy flux through the eddy's boundary. So in this term, UC is the velocity of the boundary and U is the velocity of the flow. This term will be 0 if the eddy's boundary is a material line. That means that the boundary of the eddy is freely advected by the flow. The pressure force work in the case of the mesoscale stable geostrophic eddy is going to be 0 because the flow is always perpendicular to the pressure gradient. Now the wind stress work, again, which will be computed using the feedback of the current on the wind stress, and the turbulent diffusivity are going to be probably the most important terms. I'm not going to talk about dissipation, which is the conversion of mechanical energy into heat, and it's going to be negligible at the scales we are considering here. So let's apply that to the Gulf of Mexico. This schematic view shows the loop current entering the Gulf through the Yucatan Channel, exiting through the Florida Straits. Sometimes these large loop current rings detach and they drift through the Gulf until reaching the western boundary where they used to be believed to decay. The previous image of the life cycle of these eddies was that they would just cross the Gulf intact and then die on the western boundary. On the right-hand side, you can see a glider section of temperature and temperature anomaly, so that you can see that they have very, very strong heat temperature anomaly reaching 9 degrees at about 200 meters. These are transporting a lot of heat and salt too. It's pretty complicated to be able to estimate in a quantitative way how these eddies decay. And one way to do it would be with in situ data. You could have a ship going back and forth across these eddies for a year, but that would be extremely expensive and very hard to plan because we don't know when a loop current ring is going to detach. So the approach I chose was to take advantage of satellite altimetry and Argo data and to use the gravest empirical mode methods. The gravest empirical mode methods is basically the idea is to build transfer functions that will associate to each couple pressure SSH, one single value of temperature and salinity. If you look at the two temperature and salinity sections on the right top side of the screen, there I just took all the Argo data from the Gulf of Mexico and I sorted it by steric height. And you can see already that there is a very clear pattern emerging. You see all the isotherms sloping down towards higher SSH. The salinity maximum also is sloping down. So this is a very consistent pattern. So if we apply to that, if we fit spline interpolance to these maps, we get what we call the gravest empirical mode. So we get these transfer functions that are on the bottom right-hand side. So now with these transfer functions, I can use any two-dimensional SSH map and reconstruct the 3D structure of temperature and salinity in the Gulf of Mexico. So I identified 40 eddies detached between 1993 and last year. The criterion for the edge of the eddies is the maximum velocity control. So it's a Eulerian criterion. I will discuss this a bit later, the caveats of using such a boundary definition. But basically, we were able to reconstruct the structure of all eddies detached since 93. Here are a couple of examples of the temperature and salinity structure reconstructed from the GEM method. On the right-hand side, you can see also the geostrophic velocity. On the right, I validated this reconstruction method using glider observation. So we had 2 glider survey across a loop current ring. So here you can see depth average temperature and salinity anomalies in blue and red, as well as depth average geostrophic velocity in black on the bottom plots. And so the dashed line are the reconstructed ones, and the plain lines are the glider observed, or maybe it's the opposite. So you can see that actually the reconstruction method from altimetry and the transfer functions works very well with an agreement, a coefficient of determination of 0.91 to 0.94. That is a correlation coefficient that is always larger than 0.95. So the GEM is doing a very good job in estimating temperature, salinity, and geostrophic velocity in these eddies. So now we have this reconstructed field velocity and heat and salt fields. We can estimate on a daily basis for all 40 identified eddies how their heat content decays with time. So here you see the trajectories of these 40 eddies, and the color code is the percentage of the heat relative to their initial heat content. That is the heat content they had by the day they detached from the loop current. So you can see that they start losing heat very early in their life cycle. And when they reach this so-called eddy graveyard, most of them have only 10% of the original heat left. So on the right-hand side, you can see heat and salt versus time, as well as heat and salt versus longitude. You can see that after 200 days, which is basically the time it takes to reach the western boundary, they only have 25% of the original heat content left. And this corresponds here to a latitude of about 94. So that's even before the western boundary. So these eddies, they lose heat and salt early in their life cycle. Now let's look at kinetic energy and how it decays. You see exactly the same pattern. Energy decay starts early in the eddy's life cycle. On the right-hand side, you can see the normalized mechanical energy averaged over all the 40 eddies. So we have time series and mean normalized energy against longitude. And it's even more striking. After 100 to 180 days, these eddies only have 25% of their total mechanical energy left. And this is long before they reach any western boundary. So this is maybe a more schematical view. So red on the map means 100% of mechanical energy, blue means 10%. You can see that energy is lost in the inner basin. On the right-hand side, we have the time derivative of energy. So that this is the rate, the decay rate really. And you can see that actually the decay rate is faster on the eastern basin and in the interior that it is in the western, near the western boundary and in the western basin. So I wanted to estimate the effects of wind current interactions on the eddy's energy. I'm going to go quickly on that slide because it was largely explained already by Lionel just before. So basically we used relative wind stress. So when you integrate relative wind stress with a constant homogeneous wind over an eddy, when you integrate the work of the relative wind stress, you get a sink of energy always, whatever the sign of the eddy is. We are also going to look at Ekman buoyancy fluxes, which are going to convert potential energy into kinetic energy. So the Ekman pumping we use is the nonlinear Ekman pumping that was introduced by Stern in 1965, and is also related with the fact that the wind stress is asymmetric and it is stronger on one side of the eddy than on the other. So on this plot, in red, you have the time evolution of the mean kinetic energy, and in blue, you have the energy loss through wind stress work, that is integrating wind stress work with time, with respect to time. And you can see that it's strikingly similar. And the evolution of kinetic energy is basically the evolution we would expect from wind stress work. But that's tricky because if we have relative wind stress, we might have Ekman buoyancy fluxes. So we might have energy conversion. So directly comparing kinetic energy with what should be expected from wind stress work is not the right way to go. And we should just be looking at, the decay of total energy, because we know that there might be some energy conversion. So here, don't look at the green triangles and the blue squares. I should have removed them. I'm not going to mention them today. So in red, the red dots, they are the evolution of total mechanical energy with time. And the green lozenge, they are the effects expected from wind stress work over the eddy. I should have stated before that I'm using scatterometer gridded wind fields. So you can see that in the end, wind stress work is about responsible for a third of the total mechanical energy loss. Now, if we look at the Ekman buoyancy flux and the time evolution of available potential energy, so the red dots is available potential energy, the blue square is what is expected from Ekman buoyancy flux. And this time, there's no trick. You can really see that all losses of available potential energy, which is not a pure loss, it's just a conversion term again towards kinetic energy. It is completely controlled by Ekman buoyancy flux. So it's really the feedback of the current on the wind that is controlling the decay of available potential energy. How much time do I have left? 0. Okay, well, if you want to ask me questions on how it goes when we use Lagrangian objective eddy framing methods, I would be happy to discuss that. But just going to show this slide, when we take Lagrangian coherent structure-based eddy boundaries, well, the wind stress work does not participate anymore to the mechanical energy decay. But this is really work in progress, the Lagrangian part. So, but I will really love to discuss that with anyone later. Thank you very much.
Stay up here. So now we can have our panelists come back up and ask a few questions. And so I think the first question should come from Chris Roberts, who's online. So Chris, you can go ahead and unmute yourself.
Hi, can you hear?
Yes.
Okay, so this is a question to Lionel. Thank you for your talk. So just as a bit of background, so the ECMWF operational atmospheric analysis already, it sees the currents from our ocean analysis to calculate the relative winds. So with that in mind, what are the implications of your work for what I would call forced eddy-rich ocean model simulations driven by reanalysis winds, which in the future, maybe from coupled reanalyses that have already felt one particular realization of the ocean currents and wave fields that will then differ from the model that is being forced?
Yeah, that's a good point. Actually, it's something actually we looked at in our 2020 paper, James paper. So that's right. That the issue is that you may double account the large scale effect of the current feedback if you use the relative wind in the forced ocean model, then because you already have it in the reanalysis. But then so if you don't use current feedback, then you won't have the mesoscale eddy killing effect, because the eddy from the reanalysis won't be at the same place than in the ocean model because it's chaotic. So basically what we would have to do is to have access to the sea surface currents that have been seen by the reanalysis, and then using the coupling coefficient, S2, the coupling coefficient between the surface current and stress, we can kind of clean up the wind, the wind and the stress, and then come up with a kind of clean forcing that does not contain anymore the imprint of the surface current. Is that clear?
Yeah.
So basically,
I mean, I get
a very short response is that you guys we have to provide the surface currents so that then we can remove their effects on the stress and on the wind.
Yeah. I mean, I guess it's not the only inconsistency, because there must be similar problems for things like sea ice, where have a big impact on the atmospheric analysis, but will be different. Thank you.
Yes.
Great. Yuri, you want to go next?
Hi. Great presentations. I have two quick questions. One to Luna first. I really like the way that you presented that 2D diagram of wind stress curve by a function of the Rossby number and crosswind SST gradient. But I got curious why you have such an asymmetry in terms of Rossby number, and if it's something more regional, or if or how you would explain that you have more points in the anticyclonic part instead of the cyclonic part.
I think for my vorticity plot, I did vorticity over the magnitude of F, so it doesn't take into the sign. So I think we have more vorticity in the cyclonic part because it's the Southern Ocean.
Oh, okay.
Right. If it's in the cyclonic part, then it could be like some mesoscale dynamics, or in the scale we're currently resolving, I suspect it's semi-geostrophic. It's like the slumping of the fronts towards like the cold part, and it's
All right.
yeah.
All right. And the other question is to Thomas, I'm sorry. It's just that I'd like to have a word about the definition of coherence in your work. And I think you kind of showed a little bit of a Lagrangian framework for that. And I'd like to have a little bit of sense of how you think that this is going to change the results if you take into consideration the Lagrangian coherence of the eddies.
Sure. What I showed earlier with the mechanical energy evolution equation integrated over the boundary of an eddy, there was this flux term through the boundary that is related to having a Eulerian criterion. If you take Lagrangian coherent eddies in the real sense of Lagrangian coherence, that is that nothing is supposed to escape or get in, and that you can only assess using Lagrangian coherent structure methods and what they call objective eddy framing. So if you remove this term, you're only left with wind stress work and turbulent diffusivity. What happens, Lagrangian coherent boundaries are usually located far inside eddy's cores, that is far away from the velocity maximum that is located at the periphery of the eddy, and which is an area where you have a lot of mesoscale straining from the surrounding geostrophic turbulence. So this is also the place where the wind stress work is going to be very strong, just in this high velocity annulus. So if you go inside the eddy's core, in the boundary that is going to be really coherent, you don't have this strong flow anymore. So basically, relative wind work is almost equal to absolute wind work. And this is the reason why when we go Lagrangian, we lose this impact of wind stress work.
Great, thank you. I think Jacob's next. I'm gonna come over here next.
Question for Luna. Very nice talk. I'm curious about the use of SST gradient as one of your diagnostics, particularly as we go to the sub-mesoscale, because many sub-mesoscale features are associated with very large gradients, but really small absolute change in temperature. And it's never been clear to me whether we really expect extremely large responses when you just shrink the length scale, but maybe you have 1/10 of a degree change, right? And so I'm curious whether you see evidence of that in your analysis, like some dependence also on absolute change in temperature rather than pure gradient.
That's a really good question. I don't think we've specifically looked at SST's response to like the winds or wind stress, but in Udi's study in 2022, I think they look at the relationship between SST and the wind stress curl and stress divergence, and they find that it's related to like the wind speed. And so if like the wind speed is stronger than like 6 meters per second, I think, and they would expect something to do with the SST gradient, but if the wind speed is smaller than 6 meters per second, it's actually the SST, or like the Laplacian of SST has something correlated with the wind stress curl and wind stress divergence. But personally, in our analysis, we haven't looked at it yet, but it's a good suggestion. Thank you.
This is for you?
Yeah.
Right. I was curious if your data is good enough to identify atmospheric stability effects. Let's say you have a really hot day with low winds. Do you see something different than high winds at night, let's say, something like that?
Yeah, so in this model, we do have like hourly resolution, and this is a coupled model, so it does have like the thermodynamics and dynamics effects folded in, but I haven't looked at the diurnal cycle and things here. But as I said, the study by Udi at 2022, they are using the same simulation as we're using right now, and they did see when the wind speed changes, there is a response in the SST or like the Laplacian of SST with the wind stress fields. Thank you.
Okay. I have a few questions for Lionel and Luna and Thomas as well. My first question is, Lionel in his paper talks about re-energization, and the re-energization of the eddies causes 15% change in eddy kinetic energy. I was wondering how much would it change the wind input? Would it change the wind input by 15%, or it would be somewhat different from the difference in the eddy kinetic energy?
I'm not sure. Do you mean if we neglect the wind response?
Yes.
Okay, yes, then if you neglect the wind response, you have an overestimation of the wind stress and of the eddy killing effect, and by about, roughly speaking, 15%, something like that.
There is 15% change in the kinetic energy, but what is the change in percentage of the flux, the momentum flux?
The flux, I don't have the number in mind, but I would say roughly 10%, something like that, roughly.
Yeah, okay. My second question is, we know that there is the seasonality of the mesoscales is lagging behind the forcing. Do you consider like the eddy killing to affect the seasonality of mesoscales? Would eddy killing affect cause the lag of the mesoscales because it is extracting energy from the mesoscales?
Well, the eddy killing effect, the efficiency of the effect mainly depends on the wind. So the larger the wind, the larger the coupling coefficient and then the extraction of energy. But I guess if you, to respond to that, you should also look the baroclinic and barotropic conversion of energy to have the complete pictures. So it may go to this direction, but it may not be the only driver.
Okay, and my third question is for Luna and Lionel. I'm sorry. So for the coupling coefficient, when you take, let's say, if you use some kind of Okubo-Wisp parameter and separate the positive and negative vorticity, or maybe look into the regions like in where the wind just crossed the landmass, maybe the wind accelerates as soon as it crossed the landmass, and there may be divergence of the winds because it's crossing the landmass, or if it is approaching the land, the wind may have convergence as it comes near to the wind. Does that affect like the background wind stress curl, or the convergence and divergence of winds because of the landmass affect the coupling coefficient or not?
For me, okay. So I have a look at places near the land mass, sorry. But then we did do some analysis to use Oberkoves's parameter to separate out like strain-dominated region or vorticity-dominated region. And we find that if in a vorticity-dominated region, the coupling coefficients we found are like pretty much similar to the domain average one. And so I feel like if you want to get a domain average sense of what's happening with wind front interactions in a certain area, you can just sample on like eddy centers or something. But we did center on filaments or strain dominated region, and we find a great increase, like about 20% increase of both the vorticity and SST gradient coefficients. So I feel like depending on the sampling area, you would get different intensities of the coupling.
My last question is for Thomas.
I just wanted to add a small comment. For example, for the US West Coast, because of the wind drop-off, so the wind drop-off is mainly driven by the orography and the coastline meandering. In that case, yes, it will have a strong effect, a kind of spurious effect on both the thermal feedback and the current feedback. So if you look very close to the shore, the coast, you really want to pay attention to other factors that may drive actually the coupling coefficients.
My last question is for Thomas. When you showed the energy budget equation, you had the wind forcing term as U dot vertical gradient of wind stress. So I was thinking, because like the wind velocity, the ocean currents, that is It is not a Kolmogorov scale ocean current. And the wind stress, of course, is from the bulk parameterization, which uses Prandtl missing length theory. Should it not also have a subscale wind work, a kind of like the turbulent parameterization for the wind work region, some subscale wind work that is nonlinear, because the current and the wind stress is not fully resolved, whatever length scales we choose.
Could you repeat the question, please?
Okay, so the wind work is tau.u. The u is not Kolmogorov scale, and tau is from bulk modulus. So it's a bulk formulation of the wind stress. It's not fully resolved to the Kolmogorov scale. So if we are not resolving up to the Kolmogorov scales, then there should be some subscale wind work similar to the turbulent parameterizations, right? So would it not affect? Because like I think Lionel said that the subscales has like a very important and very large wind works. So it may go up to very small scales, maybe the scales of like hours or maybe minutes. So should we not parameterize those in the budget equation?
As for now, I've been only looking at this through the lenses of altimetry. So with a pretty coarse resolution of 1/4 of a degree, but with an even much larger decorrelation radius. No? So these are terms I cannot access, unfortunately. So I guess you're right. But the thing is, that's about the best I can do so far. But this kind of thing should be studied with high resolutions model rather than with, this coarse altimetry, which is only meant to bring some observational evidence and quantification of these effects, but of course, which has biases due to the coarse resolution. But I think you're definitely right. Yep.
Thank you very much.
So, you can come in a second. I was just going to say, Thomas, I mean, the nice thing that I like about your approach is that you also are comparing the residual and the time series. So if those effects are systematic and large, you would have seen it in that final comparison, even though you can't directly detect them.
Exactly. The only thing I can do is compare terms and see if they make sense together. I cannot have definitive conclusions about the dynamics. Just I see the energy evolve in a way that is consistent with, say, Ekman buoyancy fluxes when I'm looking at available potential energy. I cannot say anything more than they are the same, but I don't know.
Yeah, I had a question for you or Luna, and I think also Lionel might have some comment. But from what I understand from some of your plots, you were showing the current feedback was very small. You had these plots and the current feedback was small and the thermal feedback was very large. And I was slightly surprised by that because I was thinking, well, the vorticity in the sub-mesoscale features is quite large. Can you explain a bit more? And is that a typical situation or is that an unusual situation? Or can explain a bit more why you had such a big difference in the thermal feedback and the current feedback, or did I miss something?
Yeah. It's a good catch because the one I showed is just from one snapshot. So it's like 1 hour. In that hour, current feedback is so much smaller than the thermal feedback. But as I show for the time series of the coefficients, sometimes current feedback does pick up and becomes way more stronger than the thermal feedback. And the strength of it could be related to the wind speed and the air sea temperature difference for like the ether feedback. And besides these like instantaneous or like besides these like hourly variations, we also see some seasonal variations for these two feedbacks. And so the results I show are from June, July, January, which is winter season in the Southern Ocean. And we see like current and thermal feedback, if we do an average, they are pretty much have the same order of magnitude. But in summer season in the Southern Ocean, we see thermal feedback is so much stronger than the current feedback. So they do change. And that's just one example.
Yes, I think also you may explain it by basically the stress anomalies induced by the current feedback can be approximated as S-tau, the coupling coefficient, time UO, the surface currents. And the coupling coefficient depends on the wind. So if you have a weak wind, you will expect to have a weak response too.
All right, we're supposed to be out of time. So we have a break now, and then we are reconvening for poster sessions at 14:30. So a half hour past the hour for those who are online in whatever time zone you're in.